Welcome to the first episode of Watch Us Lose Our Minds Trying to Understand Simple Shit.
Is that the name of the podcast then?
Negative. I just thought
it's a long title, guy.
Yeah, no, it's more of a parody title. Yeah, it was definitely not a serious title, okay? But it's likely an accurate description of what's going to happen. So I think first things first would be sort of to get an idea of where you guys are at, if anything that I've previously mentioned made any sense, if that picture was just like, what the fuck is any of this, etc. So if you wanted to start with a brief sort of overview, I think Justin's probably going to be the briefest of the overviews, so we might start with him.
Yep, ground zero, start all over.
Do you understand anything?
No.
Okay. Glad we got clarification on that. Polska, you?
No, legit. Like when you brought up this idea and you mentioned that our parts in this episode were going to be to listen intently and ask questions to try and sort of get you to talk more about it, to teach us exactly. I don't even know what the topic is actually called. I think it's ruliology. I think that's what we're going to be talking about today, but I'm not even sure. And the guy's name, you mentioned some guy's name before. That's all I know.
So, nice. So we're really starting from ground zero. Okay. Yeah. This could be an interesting adventure. So the guy we're referencing is Stephen Wolfram. He is of the gentleman who sort of invented Wolfram Alpha, which was the sort of first successful attempt at a computational knowledge engine. So what that means in like simple terms is you can ask it questions in real like language and it'll give you outputs essentially. So you can ask it what the temperature is somewhere and it'll interpret that natural language, input and then give you the temperature for the place you queried. It's interesting because it's like the back end of Siri and Alexa. That's how they sort of got their products to market, is using Wolfram Alpha. It's also phenomenal for like maths problems and a whole bunch of other stuff. Anyway, it was really interesting because he was the first person to really be able to turn natural language into like computer understandable code, so to speak, if that makes sense. Anyway, he, at the beginning of the pandemic, started a project to understand the fundamental theory of physics using some things that he discovered many years ago and published in a book called A New Kind of Science. And so he's been on this quest for a long time. He was a high energy particle physicist at like a very young age. He worked with Richard Feynman and a whole bunch of other people, and he's been like heavily involved in mathematics and physics for a very long time, but subsequently got into computational computers and then started developing computer languages, for which he has his own computer language called Mathematica. And it essentially uses symbolic transformations to do computations, which is like a really interesting concept. We'll get into all this a bit later. So in like to sort of intro the whole thing, like essentially what we're trying to do here is understand what anything is. Right. So we take for granted that, tables and chairs exist, so to speak. Right. And we're like, yep, tables and chairs exist. They're objects. And then you can go, okay, well, what are tables and chairs made up of? Right. So they're made up of these molecules. Okay. So what are molecules made up of? Well, molecules are made up of atoms. Okay. And then so the next logical question is, what are atoms made up of? People say that they're made up of protons, neutrons, and electrons. There you go. Okay, cool. What are protons, neutrons, and electrons made up of? And then you get down into quantum mechanics, and it turns out they're made up of up quarks, down quarks, charm quarks, and all these funky sounding things that seem very abstract. And that's essentially the furthest we've gotten. Okay. But the world down at that quantum scale appears to do very strange things. So one thing we can start to intro is, what's the difference between sort of general relativity, which is space-time, the way that we perceive it as human observers, and quantum mechanics? So do you guys have any sort of insights into that, or any sort of understanding, or if like you have a brief, I don't know, summary of what you might understand about those things?
between quantum mechanics and relativity?
Yeah. So general relativity is kind of like what we experience at the scale that we exist. So we exist close to like the meter scale. We're roughly, like a meter and a bit tall, et cetera. And the things that we interact with are, around that size. And then we can zoom in a bit and we go down to like a molecular scale, which is a lot smaller. And it's kind of hard to see those molecules individually. But when they get aggregated together, we can perceive them to be objects, And then if you zoom into a molecule, there's these atoms that we can't see with our naked eye. We need microscopes or electron microscopes to be able to see these things. So these things exist at different scales. And so as you go down the scales, you eventually go from general relativity, the scale that we exist at, to this quantum scale. And that seems to be the base level. But lots of really weird stuff happens down there. And it doesn't seem to align with what happens at the top. So essentially, one way I found useful to sort of think about this, and I'll just share my screen.
Yeah, basically, I have no prior knowledge regarding relativity or quantum mechanics, guy.
I haven't taken physics since grade 10, guy.
Yeah, that's the last time I've taken physics as well. So
hilarious. Okay, cool. So we'll have a good place to start. We'll be able to go through the whole shebang.
Polska, do you want to just quickly tell him what you learned in physics?
When I learned in high school, in general?
Yeah.
Basically, I learned how to sleep with my eyes open. So what I would do is I would focus it on the teacher and they'd be speaking. And after a while, I would just hear like this buzzing sound and I would just be like gone. Like physically I was there, but like, yeah, it was weird, man. And like suddenly the class would be over and be like, holy fuck, like where did I just go right now? Yeah, it was it got to the point where one of my teachers actually called my mom. I remember this. It was my grade 10 English teacher. She calls my mom. She's like, yo, I think maybe you'd like to bring Daniel somewhere to get checked out. And my mom was like, the fuck do you mean checked out? She's like, yeah, like Daniel's having some issues in class, concentrating on the lesson, being present. So
I'm crying.
So hopefully it's a new experience for you this time around.
Yeah, well, since then I actually became very interested in learning, but like high school, I was a completely different person, obviously.
I'm glad to hear that. Okay, so with all of this, we're essentially just trying to understand what anything really is, right? So if you ask enough questions, like we can observe certain things and see that things happening, but if we ask enough questions, you end up going down this scale, and at some point it kind of stops, right? And the furthest we kind of got to is quantum mechanics. But in quantum mechanics, things seem really, really odd. And so the easiest way I've sort of found to think about this is the following. So let's go to this quantum mechanics. So we observe things such as each other. We call those entities people. We can observe objects such as tables and chairs. We can see that those tables and chairs are made up of other things, namely molecules. These molecules are made of atoms. Atoms are observed or said to be made of protons, neutrons, electrons, and those are said / observed to be made up of quarks, down quarks, charm quarks. But that's where the story kind of ends. And these quarks are said to be quantum mechanical. So what does it mean to be quantum mechanical? So the easiest way I've found to understand quantum mechanics is to think of the difference between general relativity or GR and quantum mechanics, which we can refer to as QM. And so in GR, things follow a definite path. For example, when you throw a ball, we can use equations to figure out where the ball will go and what path the ball will take. Essentially, we can predict what will happen given some information about the initial conditions, right? So that kind of makes sense. Like we know that, like, okay, when you throw a ball, it follows a definite path. And if I position myself here, and I can catch that ball, right? That all kind of seems very intuitive to us as humans, right? Yeah. Awesome. This is like actually teaching a class where the students don't actually give you much feedback. Nice. So in quantum mechanics, things follow all possible paths. And so in the case of quantum mechanics with the ball, instead of following a definite path, the quantum mechanical ball will follow all possible paths. Right? And that seems really, really counterintuitive. It seems really odd because when we see things happen, we see definite things happen. Yeah. But in quantum mechanics, it says that all possible things happen. That kind of makes sense, even though it doesn't really make sense.
Yeah, it does make sense, even though it doesn't make sense, like you said. There's a connection missing. Going back to your example where like in relativity, like things that we see make sense to us as we see them. But at the lower level, you said quantum mechanics level, the rules change and there's like a separation between the rules. Like there's a misconnect.
Yeah.
Am I on the right track, Rubes?
Yeah. So we struggle to explain that because when we observe things in reality, we observe definite things happening. Well, that's what we think. We think we see definite things happening. But when we look at quantum mechanics, it's like all possible things are happening. Okay. And it just like breaks our minds. And so there's these famous experiments. One of them's called the double slit experiment, which I can get a picture up of as I'm screen recording. So we can have a look at this. So it's like a very famous experiment that shows the weirdness of quantum mechanics. And essentially, like a decent example. You guys kind of see that?
We can see the image, yeah. I don't know what the fuck it means.
Well, so they're saying that there's like, we've got a photon sort of emitter. Yeah, this might be a bit better. So something's emitting photons and we set up a sheet in the middle that has two slits in it, right? But we're only sending sort of one photon at a time, right? And you would expect that the photon would either go through one or the other. But what it ends up looking like is that photons go through both or no photons go through both kind of thing. And so there ends up being this interference pattern, right? Whereas you would think that this would be scattered with photons all the way along.
Yo, Rube, sorry to interrupt. Is there anything on your desktop that you don't want people seeing?
Nah, it's all right. But I'll cover that up for now. So what it's saying is that there seems to be this sort of interference pattern, or that like things should show up, but they don't end up showing up. Right. And so this is like a really strange thing. And we can get back to this whole topic once we go through some other concepts. It'll kind of make a lot more sense. But it's essentially like quantum mechanics is very weird and unintuitive to the human mind. That's the main sort of takeaway. Yeah.
Sorry. So, right. I understand that. Right, but this example here, basically, we would expect that on the black wall, there would only be two slits of light, since there's only two slits on the gray wall.
Yeah, that's one way to say it. Yeah, definitely.
But in quantum mechanics, because all possibilities are present, that it's possible to see many slits of light show up on the black wall.
Yeah, that's a way to describe it. Yes, we can get more technical and sort of get and better define the terms and be a bit sort of more precise with the language as we go through this and get it. But essentially, at a high level, that'll do as an understanding for now.
Guy, flash that second, the top left second row image.
This one?
One over on the left.
We'll go to the link.
All right, never mind.
This one? Yeah?
Yeah, that's what I was. I just wanted to see what it looked like. That's all.
You good?
Sure.
Okay, cool. So we'll come back to some stuff like this once we go through it. So we need to talk about like essentially we'll start talking about the Wolfram model, but before we go over the Wolfram model, we sort of want to understand what it really is. And so at a very high level, it's just a way of talking about the universe or modeling the universe that appears to be very, very useful. Okay, so it starts from a very few assumptions, and all of the things that we experience in reality and space-time and all this other stuff, quantum mechanics, everything emerges out of that model. Okay, and so most other models, you have to put these things in. Right? You have to be very specific to define dimensions and define what you're really talking about in order to sort of get answers. Whereas with this, you start from like the bare minimum, and these things emerge out of the sort of interactions of the bare minimum, so to speak. Okay. So in this, his model is a graphical way of representing this. Okay. And so the graphs that he uses are called hypergraphs. And a hypergraph is essentially a graph that can have any number of edges or just connections to other nodes. So when we're talking about graphs, we have nodes, which are the points. Okay. And the connections between the nodes are the edges. Yeah. And so a hypergraph can have n edges, which is just any number of edges. Yeah. Got it? Cool. So, hey,
that makes sense. Yeah.
Yep. Okay. So, this is like the sort of basic, how can I make this? Yeah, there we go. So graph types, right? So you've got single evolution history graphs, graphs that are obtained from particular evolution histories, with particular sequence of updating events. For rules with causal invariance, the ultimate causal graph, let me move you guys, is independent of the sequence of updating events. So bunch of words there, doesn't really matter just yet. We can go over it a bit more detail. So this is what's called a spatial hypergraph. Okay. And so you can start from very small initial conditions and sort of run that, and it evolves into something like this, but this is only probably after about 10 steps. And so you can imagine, after, millions, billions, or trillions of steps, this thing would get incredibly complex. Right. So we'll don't have to understand a heap with this. I'm just sort of giving you a pre-frame into this. So then we can go down into a different type of graph, which is a causal graph. And so this is specifically a space-time causal graph. So this is a graph with nodes representing updating events and edges representing their causal relationships. So this sort of explains, like, that GR level, we see cause and effect between things. And that's kind of how we understand general relativity. Yeah. So as observers, the size that we are in the universe, we can only really tell causal relationships between things. Yeah. That's why GR is so intuitive to us, right? Because that's how we perceive the universe, or that's how we pass the universe.
I don't even know what GR is, general relativity.
Yeah. So that, that term we defined just like 5 seconds ago.
Well, I mean, you didn't tell me that there was an abbreviation for it. So catching up here, guy.
Okay. I apologize for that. Polska will check the audio recording to see if I did or not. Yep. But yeah, GR, general relativity. Okay. QM will stand for quantum mechanics moving forward.
Thanks.
If that helps. So this is essentially a causal graph. So this is a graph where you can see that this node here causes the event here to happen. This event here causes this event to happen. And then these are all causal connections between other events that are happening. Okay. Yeah, it's going to seem pretty abstract to start with. And then this is a multi-evolution related graph. So these are graphs obtained from all possible evolution histories following every possible sequence of updating events. For rules with causal invariance, which is a term we'll learn in a minute, different paths in the multi-way system lead to the same causal graph. Okay, so it says, like, no matter that there's all these different paths you can follow, right, at the end of the day, they're all going to sort of end up leading to the same point.
I don't know how you got there.
Well, so I explain this, right? So think to yourself, no matter how much you learn about physical activity, no matter how much you read about how good the benefits of physical activity are, you're still probably not going to be physically active.
That felt like a dig, guy.
I thought I would not miss the opportunity to analogize it to something very close to our hearts. But no, does that kind of make sense? So it's like, no, you can follow all these different paths, but at the end of the day, the same outcome is going to end up being the same. Like it's going to end up being the same outcome.
Well, I mean, I understand how that could be in the example, but I don't understand in this graph how that's the case. Like I understand like knowledge might be a poor predictor of behavior, but how does that relate to this evolutionary graph?
Well, so what we're saying is following every possible sequence of updating events. So this will sort of get us into rules and things like that. So we can get into that now. What causal invariance is saying is that, okay, so if we have a set of, I don't know if this would be the best place to start. Maybe we should just go over it. Okay, yeah, let's get into that. That was the sort of last. Yeah, there's a couple more graphs to go over. Let's dig into this.
Go through the graphs.
We'll go to the graphs, then we'll go down and dig into it. Okay, yeah. So this is multi-way states graph or a multi-way graph. And this graph represents all possible branches of an evolution for the system. Okay, or of evolution for the system. Each node represents a possible complete state of the system at a particular step. Each connection corresponds to the evolution of one state to another as a result of an updating event. So think of an updating event as when a rule is applied. Okay, so when a change happens. The multi-way graph potentially represents all possible paths of evolution in quantum mechanics. In a causal invariant system, every branching in the multi-way system must ultimately reconverge. And so that's essentially saying that even though you've got all these branches, right, if it's causal invariant, all those branches eventually will end up merging into one event or one state of the universe.
So at that point right there, that's what I'm confused about.
Yeah.
How, okay. Because
yeah, keep going.
You could have all these variations of outcomes, right? It's essentially, it could be infinite. As soon as one variable is introduced, we have an infinite amount of possibilities. So how is it that in the end they can all converge into, it's like the same thing, like they converge into the same thing with one result?
Essentially it's like you throw the ball follows all possible paths, so to speak, but at the end of the day, the guy catches the ball.
Okay, so this is as it pertains to general relativity.
No. So we're way down in the weeds here. This is the multi-way graph, but I was just using that as an analogy to try and sort of, bootstrap it across. This is essentially saying that, even though you can follow all these possible orders of updating or all these different rules could be getting applied, eventually, like at the end of the day, they're all going to end up being the same thing. So what it's saying is, or one thing that it's saying is, you can have lots of different rules, but as you're applying them, they sort of end up resulting in the same outcome.
Okay.
So you can have sort of like these intermediate states where it's like going down all these possible paths, but at the end of the day, the board can So a good way to jump into this is to sort of look at games. Okay, so let's go and have a look at that.
Sorry, Rubes, I just have another question.
Yeah.
You used the throwing the ball as an example. So although many variables might come into play, the ball will always come back down to the ground, right? That's what your example was?
That was kind of like a bad analogy on my part.
No, it's all right. Can you try and give another one, something else? Because I mean, I understand that one, but I'm just trying to apply.
Okay. Here's a stab at one. You try and do all these things to improve your health. You try and do all these different things to improve your health, your physical activity, your strength status, all these different things. But at the end of the day, you end up dying. Right. So there's all these different things you can do in the interim, right? All these different ways you could go about it. But at the end of the day, you end up dying. And that's that.
That was actually the one, right? When you began explaining it, that was like one of the first things that popped into my mind is when you were explaining it. Like, Yeah, that no matter what we do, we're just going to end up dying. And no matter what happens, the world will end one day. The world will end one day. Is that like an example too?
Yeah. So essentially, like ending? When the sun explodes, the Earth will no longer exist in the way that it is. So yeah, that's one way of saying it. Look, whether or not we will all end up dying, historically that's been true, but it potentially isn't true. But there's all these like crazy implications. So we'll get into this kind of stuff. Like these are the cool conversations we can end up having once we sort of get a better understanding of the model and what it sort of implies. We can end up having these really interesting philosophical conversations about all of this stuff. So that it'll give us the tools to do that. Okay, so Wolfram kind of has this. Let's do it. Wolfram.
You're going to finish off those graphs, Guy?
Oh yeah, sorry. My erraticness has got the better of me. Okay, let's have a look here.
So like the end of that graph is legit the inverse of what we see right now.
What do you mean?
Like the end of this graph is like if in the end there's only one outcome, it eventually will be the inverse of that, no? Like
yes, yeah. What it's saying is
mirror that.
Yeah. So what it's saying is this isn't always the case. This is only it only merges again when the system is causal invariant. Okay, and we can get into causal invariance. I have a good little work note on that, so we'll get into that in a sec. So I just want to go through and show you these kinds of graphs. Okay, so then we have there's this multi. Hey,
sorry, Guy.
No, go. What do you want?
So not all systems are causal invariant. Is that what that's saying then?
Yeah. So there's definitely a large class of rules that are causally invariant, and then there's a large class, then there's others that aren't. Okay. And it appears that the way we perceive the universe, it has to be the case that it's causally invariant.
Okay.
Yeah. So, and we'll get deep into this sort of stuff. I just wanted to kind of give an overview first so that when we go and look at the sort of from the ground up view of it, we've sort of got some reference points. So if you're not understanding it completely, that's perfectly fine. Like, again, I don't even understand this. Like I have gaps in my understanding as well.
I think I understand it.
Okay.
It's hard to think of examples though, but
okay, this is the thing. So as we get into it, we'll be able to come up with hopefully very useful examples. Okay, so we'll move on. So multi-way states and causal graph. So this is a graph representing both all possible branches of evolution for states and all causal relationships between updating events. So each node, or these points, okay, representing a state connects other states via nodes representing updating events. So the updating events are in orange. Yep.
Yeah, I see that.
Yep. The updating events are connected to indicate their causal relationships. The multi-way states plus causal graph in effect gives complete causally annotated information on the multi-way evolution. So this is kind of a graph showing the possible states of evolution and then showing what things what things cause other things. Yeah. So that's sent through that Judea Pearl paper.
Yeah.
And that has direct relation to this. Okay. And so we'll get into how all that happens. All right. So again, we'll just keep going down. So then this is a multi-way causal graph. And this graph represents causal connections among all possible updating events that can occur in all possible paths of evolution for the system. So think that quantum mechanics, all possibilities happening. Yeah.
Yeah.
So this is a graph representing all possible paths of evolution for the system. Each node, these points here, represents a possible updating event in the system. Each edge represents the causal relationship between two possible updating events. In a causal invariant system, the part of the multi-way causal graph corresponding to a particular path of evolution has the same structure for all possible paths of evolution. The multi-way causal graph provides the ultimate description of potentially observable behavior of our models. Its edges represent both space-like and branch-like relationships and can potentially represent causal relations both in space-time and through quantum entanglement. Okay. So this is just showing like these are all, this is a dramatically sort of reduced version to get it to look like this. There's a whole bunch of stuff that they've sort of like eliminated, and these sort of edges, the connections between them is like a summary of that. But if we were to like zoom in on this, we would see much more detail. Okay. Like if we were to add the things back in and then zoom in, there'd be a lot more detail here. But this is just essentially showing you the causal relationship. So like, this has to happen for this to happen, for these things to happen. Cool.
Well, I have a couple questions that I don't understand. Well, like, why are there different thicknesses? Are they weighted lines? And the other question is, why are there multiple edges from two nodes?
So because the graph is representing like all possible updating events in the system. Okay,
yeah,
so like
there's only one. Why? Like, if you look at the one on the bottom right,
this one.
Yeah.
Yeah. So like, this is saying
why is there 25 lines going to?
Well, so it's saying
one
it can
node
go
to another
from here straight to here. Okay, or it can go from here to here to here. Yeah. So like, say there's a rule that took this from here to here. Okay. And then another rule that took it from here to here, or there was just one application of a rule that sort of went from here all the way around this line to here. And so the reason this looks funny is because in order to sort of be able to visualize this, they've had to get rid of heaps and heaps of stuff. Okay. And so these edges are kind of like an aggregate way of looking at this.
Is this trying to show that, maybe it's trying to show that between nodes that there is an infinite amount of possibilities, and they just want to simplify and not show that it's like that between
essentially
all the nodes.
Essentially that's the case. Yeah, we can be way more specific with the language, but yes, as a very like loose, yep, that's it for sure. Like they've got rid of heaps of stuff just to be able to clearly sort of show this. This isn't like once we have a better understanding of everything, this will make a lot more sense. But there's a whole bunch of topics we sort of got to dig deep into to be able to see how this really relates. And I don't have efficiently or sufficiently an efficient way of articulating this just yet. So this is something that we can do as we start to develop an understanding of it, is come up with better ways to explain these things. Yeah?
Sure.
Okay, so as we move on, this is the last one, which will be a branchial graph. Okay, and so this graph represents the common ancestry of states in the multi-way system. Each node represents a state of the system, and two nodes are joined if they are obtained on different branches of evolution from the same state. To define a branchial graph requires specifying a foliation of the multi-way graph. The branchial graph potentially represents entanglement in the branchial space of quantum states. So, have you guys ever heard of quantum entanglement?
I've heard the term, but I have no idea what the hell it means.
So say you have two quantum particles that are separate from each other, and then you bring them together so that they interact. Those particles will become entangled. And so there's a bunch of things in quantum mechanics, a bunch of experiments that have been done. And so what they've sort of shown is that if you have two entangled particles, right, and then you take one of those entangled particles and you transport it like, a ridiculous way away. And they've done this through what's called quantum teleportation, but not like in the way of teleporting people or anything like that. It's a different kind of thing. But it's essentially, it shows that's like a form of faster than light information transmission can occur. Okay. And so what happens, so you have these two quantum particles, they're uncorrelated to start with, you bring them together, they become entangled. So you take one of those quantum particles and take it really far away, and then you keep one in your possession. If you make an observation on the one that you have in your possession, you can gain information about the one that's very far away instantly. And that's because they're quantumly entangled. And what this sort of graph shows, this branchial graph, shows how that entanglement actually works and why you can have that faster than so-called light transmission of information.
So there was a transmission of information that occurred. Maybe could we think of it as a coding, which one gave to the other, and the other back to the other. So when one is really far away, and when you see a change in yours, you can be assured that the same change is occurring in the other one.
That's it. Yeah, that's
they now
essentially
have the same sort of coding.
I don't know about the coding, but what you said about because you can tell one thing about one particle, you can know something about the other particle. That's essentially what that's saying. And what this is.
So what happens? Sorry, Roops. What happens in the entanglement process that allows for that to occur?
What happens in the entanglement process that allows that?
Yeah. So when you said when one particle comes in contact with another one, they become entangled, right?
Yes.
And when you separate them, and you could have one really far away, and you're just looking at this one can be representative of the changes of happening in the other one. And my question is, how can that occur? Was there some sort of exchange of information that occurred, which makes them both identical?
No, so not both identical. What the reason it can happen is because of this branchial graph, this entanglement graph. All right. This is kind of what this tells you. And so we get into all these different spaces where these things happen. And so because they're sort of, when you entangle them, they become close in sort of branchial space, but they can be far apart in physical space. So you can tell one thing when you observe one, you can infer information about the other thing, even though it's very far away. And that information couldn't have been transported fast. Typically, they think that it couldn't have been transported or transferred faster than the speed of light, but it does. And so that's this branchial space explains that, right? And so this is where he references the branchial space. Okay. So again, we don't have to fully get this just yet. As we go through these things, they're going to become a lot clearer. Yeah. But I just sort of get the basic ideas. Yeah. But because they're entangled, they're sort of deeply connected still, if that makes sense, right? There's a connection between them. It isn't in physical space, but it's in branchial space.
Okay, but for that to occur, there must have been some sort of exchange of information in between the two during the entanglement, right?
Yes. So this is like at the branchial scale that's happening.
Okay, but they don't become identical. So although they haven't become identical, how can you infer information from one that would correspond with the other one?
So it's like if I observe, they're not the same particle. Okay, so in quantum mechanics, there's a whole bunch of stuff. There's like the Pauli exclusion principle that says that no two electrons can be in the same state at any one time. And so say you have two particles, and in quantum mechanics, we talk about like their spin. Are they spin up, spin down, that kind of stuff? Okay, so if you have two particles entangled and you observe that one's spin down, well, then you know the other one can't be spin down because it can't be in the same position as that one. So therefore, you know it's kind of spin up. Okay. Right. So that's one way to sort of think about it. Yeah. Again, we got to get deep into the weeds to sort of answer your question, but these are the right questions you're asking. And we need to get a bit more of an understanding generally of these concepts before we can really dig deep into them.
Okay. So you can essentially deduce, is that the word?
Yeah, it's essentially you can deduce, but the reason you can deduce it is because of this branchial, look, the way they're connected in branchial space.
Okay.
Yeah.
Okay. Thanks, Bruce.
Okay. So let's go. What is the Wolfram model? Okay. And so a nice sort of, okay, let's start with this one. The basic concept of applying our models to physics is to imagine that the complete structure and content of the universe is represented by an evolving hypergraph. Okay. So those things we just saw before. Yeah. There is no intrinsic notion of space. Space and its apparent continuum character are merely an emergent large-scale feature of the hypergraph. Okay, so there is no space to start with. There's nothing. We've just got these tiny geometrical points all throughout space. And it's the connectivity of those points that sort of gives us the perception of space-time the way that we see it. Okay, so we go there is also no intrinsic notion of matter. Everything in the universe just corresponds to features of the hypergraph. There is also no intrinsic notion of time. The rule specifies possible updates in the hypergraph, and the passage of time essentially corresponds to these update events occurring. There are, however, many choices for the sequences in which these events can occur. And the idea is that all possible branches, in some sense, do occur. Okay, so that's kind of like a bit of an overview. I've got a different summary of a different way of describing it that says the Wolfram model does not use the continuum description of spacetime with Lorentzian manifolds. So it's math terminology. Instead, it is based on the combinatorics of relational properties of events. This makes it possible to see the computational architecture that underlies physics today. The archetypical structures that appear within this framework are called multi-way systems. Some of those graphs we saw just before. These systems are made up of non-deterministic rewriting rules with a notion of causal structure. Multi-way refers to the fact that all permissible applications of rewriting rules are possible, leading to multiple chains of rewriting terms. These chains are partially ordered by causality. Okay, so what does that kind of say to you?
I don't know. There's a lot of stuff that I don't understand there.
There was one part specifically, determining, or was it? It's really small on my screen.
Non-deterministic rewriting rules?
Yeah, these systems are made up of non-deterministic rewriting rules with a notion of causal structure. So the systems are made up of non-deterministic rewriting rules with a notion of causal structure. So it's like there's organization and chaos, basically.
Yeah, that's kind of a way to say it. Yeah, definitely. So like all we can there's all these things happening, right? But all we can really perceive is the causal structure.
Okay.
That's one way. That's a way to say it. But yeah, feel free to keep riffing on that.
No, I'm having a difficult time without actually sitting down and digesting. It's difficult to understand it this quickly. You know what I mean?
Yeah. No, I get
some of the stuff I'd have to sit down and really read it a few times and to digest it. Can you repeat what you just said, Rube? Sorry, I didn't hear you.
With which?
So after I gave my horrible example that there is organization and chaos.
No, that's seriously a way to think about it. So, with all this immense complexity, these sort of large scale phenomena appear that we can sort of say definite things happen. And essentially one way to think about that is if you've got all these updating rules, some of them will overlap. Even though they're different updating rules, when you run them enough, they sort of result in the same sort of behavior or the same sort of pattern emerges. And that's sort of why we can tell anything. Now, I think we've kind of gone over a whole bunch of words and a whole bunch of stuff like that. And again, it is really hard to take in this regard, but I want to use visuals to go over this kind of stuff. So one thing we can do is Can
I just ask clarification on one thing, Guy?
Yeah.
These updating rules, when they update in a model, right? Does that edge change, or is that an additional edge in one of these multi-way systems?
So it can be both. So I can show you some examples. So this is probably a really good intro to get into the rules and what the updating events actually are. So just as a really brief summary, we'll do this one. Okay. So the universe can be thought of as a giant hypergraph that is constantly evolving. There is no intrinsic notion of space or matter, and time is just the sequence of updating events.
Okay. Finally, I'm sort of grasping something.
Yeah. Okay. So good. And now we can sort of jump into this a little bit deeper. Okay, so let's go to now there's this is a good walkthrough that he has put up on their website. The technical introduction. We'll just kind of breeze through most of this. You guys got a big enough view of this on your screens?
Yeah, I can see it.
Can you zoom a bit?
I can.
Yeah, it'd be better for when we upload the video. Oh, that's nice.
Okay. So I'll just zoom out and then zoom back in. Okay, so let's just have a look at the basic structure. Now, be mindful, this is incredibly abstract. Okay. So these are like just, yeah, incredibly abstract things. It's really funky. Okay. But what they've been able to show is that you could start with these like initial, like nothing, and just have a collection of nodes. And then you can have these updating rules. And if you run it, you get all this crazy emergent structure and complexity and just bonkers stuff. Okay. And it's like, how could something so simple lead to something so incredibly complex? All right. And that's like kind of the amazing thing. So I'll just read the basic sort of terminology. At the lowest level, the structure on which our models operate consists of collections of relations between identical but labeled discrete elements. So that's these tiny points in space. Yeah?
Yeah.
Make sense?
Yeah.
Yep. One convenient way to represent such structures is as graphs, or in general, hypergraphs. The elements are the nodes of the graph or hypergraph, and the relations are the directed edges or hyperedges that connect these elements. Okay. So the relation or the relations are the directed edges. So how a node connects to another node is its relationship. And essentially the reason like I initially got interested in this, because I was like, oh my God, that explains context, right? It's what gives it's what gives things their identity or like their meaning or their sort of objective reality or what they appear to be is their relation to every other thing.
I still don't know what the difference is between a graph and a hypergraph and an edge and a hyperedge.
Okay, so a graph or a hypergraph. A graph is, I think that that's not necessarily the most technical definition, but typically graphs are kind of like, you know, you have a 2D grid. That's a graph structure, but you can only ever have 4 edges from any node. Yeah.
Say that again.
Well, a normal graph, they're kind of limited in the amount of edges you can have.
Okay.
Yeah. So if you have a 2D grid, think about you've got a 2D grid, you've got the points on the 2D grid, and then you've got connections between them. If it's 2D grid, that just makes squares, right?
Yeah.
Yeah. So each node can only have 4 connections. Up, left, right, down. Yeah, to make the 2D grid. But if you want to model more complex things or more complex relations, you've got to be able to have more edges that can go to each node.
Okay.
And that's a hypergraph. So essentially a hypergraph is like n edges. You can have any number of edges connecting a node. And a hyperedge is when 2 nodes share the same edge, or a group of nodes share the same edge, I believe. We'll get a more like a better definition in a second.
This just looks like a mediation model to me.
What's a mediation model?
Well, like there's no association between 4 and 3 or 4 and 2 without 1. So 1 is a mediator. It mediates the relationship between 4 and 3 and 4 and 2.
Yeah.
I have no idea if that makes any sense.
Yeah, it does. But yeah, like, so they're just interpretations. So what a mediation graph, where do you find that typically? Like where's that terminology come from?
It's we use it in behavior studies, behavioral interventions and stuff like that. So like if you had an intervention, which would be 4, and you were trying to increase physical activity, which would be 3. So you could have a direct path between 4 to 3, but you might have a mediator that strengthens the relationship or reduces the relationship, which would be a mediator. So for instance, like parental support or something. So your mediator would be in that 1 position, and that mediator can either strengthen or reduce the association or the causal effect between your dependent and independent variable.
I just want, could you define reducing?
Did I say that?
Reducing. I like that. Okay. So what you're saying is correct. And so that's just like, that's showing you how universally useful graph structures are. And that's essentially why they've been picked, because they're like the most minimal model to describe things. And so like the study of these graphs is essentially the Wolfram model. I mean, what they've been able to find out is when you have these hypergraphs and you have these updating rules and you just run all possible updating rules, all this crazy stuff emerges that also ends up like explaining quantum mechanics and general relativity and linking them together and explaining that they're actually the same theory, just at different scales or viewing through different reference frames, so to speak.
Well, I don't understand how that can be the most basic structure. Like, how isn't 4 to 1 the most basic structure?
So what it's saying here is that there isn't a direct, like 4 to 1 and 1 to 3 is showing you the relationship between these nodes.
Okay.
Yeah. So like there isn't, like, to show this representation, there isn't a more minimal way to do it.
Okay.
Like, the reason you use mediation graphs is because that's the simplest way to explain that concept.
Yeah, no, but it's confusing when it says this is the most basic structure, when you could just look at the relationship between 4 and 1. And that is the most basic structure. What do you mean? I don't understand how this could be the most basic structure. Why you have to have 4 nodes, or is this just an example?
No, this is just an example. This isn't saying that this is like what this is just saying an example, the graph. So it's showing you an example graph with, 4 nodes in it, right? And it's showing you the relationship between those 2 nodes. Okay. And it corresponds to the collection of relations that is 1 goes to 2. So 1 to 2, 1 goes to 3, 1 goes to 3. Okay. 2 goes to 3, 2 goes to 3, and 4 goes to 1. 4 goes to 1. So it's just showing you how to represent that collection of relations. Yeah. And this is just arbitrary, right? This isn't like this is how the universe started. This is just an arbitrary example.
Why the hell is 4 starting on the left too? That annoys me. I don't understand that. Why isn't 4 1?
Because the rule starts 1 to 2. So it's going to pick that as the central point. And then it's going to have this 4 to 1 is kind of like getting added into it, right? It doesn't matter about the payout or the setup of any of that. Okay. It's just showing relations. Cool.
Sure.
You're assuming that 1 is the initial thing, and it's not. Like the numbers might be a bit misleading in that regard, but that isn't the case.
It looks like in this example that 1 is initiating, because everything essentially comes from 1.
Yes. But
right?
The way that they're representing this is in the following form, and it's just showing us the relation. So the notion of like left to right and all that kind of stuff, it's not really relevant at this scale, right? We don't even have a notion of space yet. Does that make sense?
Sure, guy.
So we're just looking at this example graph, and we're showing that it corresponds to a collection of relations. Okay. And remember, like, we're building this whole thing up just through the collections of relations to the atoms of existence, right? These tiny little particles. Okay. So the order in which these relations are stated is irrelevant. but the order in which elements appear within each relation is considered significant and is reflected by the directions of the edges in the graph. The specific labels used for the elements here, 1, 2, 3, and 4, are arbitrary, right? That's the point I was just trying to make. They're arbitrary. All that matters is that a particular label always refers to the same element. Yeah? So it's saying that like all of this, the numbers, all of it's essentially arbitrary. The only thing that matters is that if we label, like if something's labeled 1, it stays the 1. Okay. If number 2, it stays 2, 3. They don't just switch their relation, like they don't just switch their numbers, so to speak. But it's arbitrary how you kind of set it up. Make sense?
Sorry, trying to find my mouse. Yeah, sure.
You both don't get it?
I mean, I understand to a point.
I understand it. There's just certain things that are annoying me that I don't understand. That's fine.
I understand to a point, Rubes, but I'm just trusting you that this is going to make more sense as we go.
Yes, it should. Okay, so we'll go a bit deeper. So let's have an example of some rules. So the core of the models are rules for rewriting collections of relations. And a very simple example of a rule is XY goes to XY, YZ. Okay, so it's essentially with this rule, you start with the position X and Y. And then if those conditions are met, you have an X and you have a Y, right? Then it transforms that part of the graph, that X and Y, okay, into X and Y plus Y and Z. So it introduces a third relation, which is Y to Z. Okay, again,
like a 3D graph.
Well, sort of like we're interpreting those as coordinate or like dimensions, but they're not dimensions. It's just numbers or letters there to represent something. Yeah. So if we keep going down here, X, Y, and Z stand for any elements. The elements they stand for need not be distinct. Okay. For example, X and Y could both stand for the element 1. The rule states that wherever a relation that matches X and Y appears, it should be replaced by X, Y, Y, Z. Yeah. So when this condition is met, this rule transforms that into this. Does that kind of make sense?
Sure, guy. I mean, like I understand. Like you're just sort of taking someone's word for it. You're like, okay, I guess X, Y, Y, Z. Sure. I don't know how the fuck they came up with that, but sure.
No, so this is the whole thing is, these are symbolic transformations. Okay. So these are like the most minimal thing you can actually have, right? Is just like this essentially, symbolic transformation. And so all that this is saying is like, you have this giant graph, okay, this giant hypergraph. And when a piece of hypergraph looks like this, X and Y, there's a rule that exists that transforms that into X, Y, and Y, Z. That's all it's saying. Like, again, it is completely abstract. It's completely funky. And what you would think is, okay, how does anything cool come out of that, right? How do you get 3 dimensions out of this? How do you get general relativity? How do you get anything out of this crap? And the craziest thing is that when you run all of the possible rules that could be possible rules, in all possible ways, you end up with something that resembles our universe. Well, you end up with the ruliad, and we're a subset of that ruliad, and that's what we perceive the universe to be. That's the crazy sort of takeaway from all of this. Okay, so we dig into it a bit more, should start clicking a little bit, right? So essentially, that's what they're starting with. It's like they're saying that you have all these points in space, right? And then all possible rules or formal systems, right? The things that could be rules get applied wherever they can be applied. Make sense or sound very fucked up?
Can you say it again, Rube? Sorry, I'm a little lost with what you just.
Remember, we're talking about the universe as this giant hypergraph.
Mm-hmm.
And the updating or time, the way we perceive time is just the updating of that hypergraph. And all that we mean when we say updating is it's the application of rules. And so what we're saying, really, this is probably an easier way to state, and this could have probably been the intro, is we have this giant hypergraph, okay? And there's these rules that just exist. And if we think of all possible formal systems, that kind of gives us the space of possible rules, right? And if you just take all of them and you say, update whatever rules wherever you can, whenever you can, right? That updating process, all of those updates gives us is time. That's the progress of time, are these updates. And what it says is, like, if you have a piece of hypergraph that looks like the following, there's a rule that exists that says turn that into another piece of hypergraph that looks like a different thing. And it's this constant updating and changing of the hypergraph that, when you run it for sufficiently many steps, ends up giving us reality the way that we perceive it.
Okay.
Can you scroll up a sec?
Guy, whatever you're reading, read it out loud, guy.
I was just trying to figure out where the fuck the letters went and why the fuck we went from letters to numbers all of a sudden.
Well, so okay. Yeah, that's a bit confusing. But essentially what it's showing is that it's just arbitrary. Doesn't matter if it's letters, doesn't matter if it's numbers. It's just showing relations. And you can pick letters or you can pick numbers, right? Doesn't matter. It's the relation between the things.
Yeah, I was just checking to see if I missed something, but
no,
for sure use letters if you're going to use letters, Steve.
Okay. So we kind of get that with this rule, we start with X and Y, and then there's a rule that says if you have X and Y in this arrangement, transform it into X and Y plus Y, Z. So it's introducing a new relation. It's creating a new atom of space, so to speak. Yeah. And so if we go down, we can see how this rule is represented. Yeah. So you have X and Y. That's the left-hand side of our rule. Make sense? This is the left-hand side of the rule.
Yeah.
Graphically represented. And then there's a transformation that occurs. There's a rule that exists that transforms this into this. So it says X goes to Y, Y goes to Z. Yep. Yeah. And so then you run it 1 time, 2 times, 3 times. You see how this graph starts to grow?
No.
Yeah.
No fucking idea.
So you have 1 goes to 2, X goes to Y.
Yeah, got that.
The order of this is a bit odd. Okay. But then you have 1 goes to 2, 2 goes to 3. So this is X, this is Y, this is Z.
Yeah, I'm with you so far. The next ones are.
So remember, the rule only takes 2 inputs, but it gives 3 outputs. Okay. So where you have a rule that has, 1, 2, okay, then it goes to 3, then you've got 1, 2, and it goes to a new third one. Okay. So that rule's getting applied again, wherever it can be applied.
Yeah. Okay. I see.
Yeah. And then you have 1, 2 goes to 4. So it's doing it again on this one.
Yeah.
Yeah. So 1, 2, necessary conditions to create the third. You've created the third. Now you've got 2 conditions. You can go this one again, or you can go this one again. So if we apply the rule, once we've got that 1, 2, 3, if we apply the rule again, we can apply it here. Yeah. Or we can apply it here. So if we apply it here first, we get to 4. And if we apply it here again, we get a 5. So you see how the graph is growing because we've taken 2 inputs, and every time we have those 2 inputs, we can transform it into this graph that has 3 outputs.
Yeah, I think I see that. So could you not put something above 3?
Yeah. The way you represent these is also kind of arbitrary. It's only the direction of the arrow that really matters. Okay. So don't sort of like worry about the layout, so to speak. Just like it's the edges that show their connectivity. So this is just a way to represent it. it isn't necessarily the best way or anything else. It's just, it's a way. And with the arrows, that's the information that we sort of care about. Yeah.
So why is the 2 to 4 arrow the opposite way of the 1 to 2 arrow?
It's not opposite. It's still a directed edge showing that 2 goes to 4. That's all it's showing. So showing that 1 goes to 2, 2 goes to 4.
Oh, okay.
Yeah. 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 5.
So can you have bidirectional arrows?
So that comes back?
Yeah, because you could have 4 to 2 to 3, no?
Yeah, but that's not what this rule doesn't apply that relation.
That would essentially be going backwards in time, right?
Sort of. So what we're following here is that when you have an X that goes to a Y, okay, you can take that as an input, and there's a rule that takes that X goes to Y and then produces a Y goes to Z.
Right. So in this rule, Y can't change back into X.
Yeah, that's what it's. Yeah, there's no transformation back to X because it doesn't have an X. It's only got to Z. So this rule creates a new atom of space whenever you've got one thing that goes to another thing.
It's essentially like time. We can only go through time forward. Is that right?
Yeah, sort of, but yeah, not like yes, but no kind of thing. But yeah, this is just showing the relation between these things, right? So if I
or like evolution.
Yeah, that's
like
right.
Evolution,
so
right?
Let's think
so we can only.
You go.
Sorry, I was just going to say that essentially evolution can only go one way. We can't. Well, actually, no, that's not in the model. That doesn't actually come true, right?
No, it's just we're getting caught up in a bunch of different things. The thing here to understand is this rule is just saying that when there's a relation that says X goes to Y, there is a rule that exists that then takes that as an input and turns it from X goes to Y to then X goes to Y, Y goes to Z. That's essentially it. And we're just looking, the arrows here are giving us the connective info between the nodes, right? That's all that there is. There's fuck all here, really. It's just very basic.
Okay, yeah, I was
just to clarify with both of you, right? So 1 is X, okay? 2 is Y. We run that, we get X, Y, Z. Z is 3. Cool?
Yeah.
Yeah, that's what we have in the second step. Then if we look for places to apply the rule again, all we need is one node to go to another node, okay? So we have that condition. We have 1 goes to 2, and so then we can run it again, and that gives us a new output, a new Z, like Z1, which ends up being 4. Okay? Make sense?
Yeah.
And then if we run it again, we've got 2 other inputs. 2 goes to 3, which could be considered our X and Y, and it gives us a new output, a new Z, like Z2, and that ends up being 5. Yeah. So we'll go through and we'll get a bunch more examples of this that will get a lot more.
The last one I don't understand. Like, I don't understand how 2 then all of a sudden becomes X for the last example.
Because these are just sort of like arbitrary representations. This X, it doesn't actually mean like a specific X, so to speak. It's just saying wherever you have a graph where there's a relation between one node to another node in this way, one node to the other node directly like that, there's a rule that exists that can take that as the input and create a new, like an output that is a new atom of space, so to speak.
I still don't understand how 4 couldn't be X then in that, like.
4 could be Y. So if you had 2 as your X and 4 as your Y, we could have another that comes off here as a 6. That's how that would grow. Okay. So with this rule, right, really, really quick, with this rule, there's 2 inputs, but you get 3 outputs. So you can only ever take 2 inputs, and the input has to be in the form of one node goes to another node. Okay. So it needs to have a directed edge, so to speak, right? So if we take 1 as X and 2 as Y, we can see that there's a direction between them. So that meets the conditions for this rule. Then if we apply it, we get the output being 3. Okay. That's our Z.
Yeah, I get how you can go 1 to 2 to 3 and 1 to 2 to 4, and then But then the 2 to 3 to 5 makes no sense to me. And then
so 2 is our X.
Yeah, no, but up until this point, it's been Y. So I don't understand how the fuck it changes. Like,
it doesn't, right? The X and Y are just arbitrary. They're just there as like placeholders to represent. Like,
so if they're arbitrary, why the fuck can't 4 be X then? I go X, Y, Z, 4, 2, 3.
Because of the direction of the arrows. The connectivity information defines the way the graph appears.
I think maybe X is like representative of the initial point and everything kind of grows from X. Is that right, Bruce?
No, it's just representing that if you have a point that's connected to another point by one edge, you can think of it as an X and a Y, but it's just a way of representing it. They're not really X and Y. They're just kind of like placeholders so that we as humans can sort of understand what's happening, even though it might be probably slightly confusing.
Yeah, I'm trying to figure out what species I am then.
Okay, so let's dig a bit deeper. It's important to note that all that matters in these graphs is their connectivity. Okay, so how they're connected, how each node is connected to each other node, that's all that matters. Okay, so where nodes are placed on the page in drawing the graph has no fundamental significance. Yeah, it is usually just done to make the graphs as easy to read as possible, which we could say that they've failed with. Continuing to apply the same rule for 3 more steps gives the following graph. Okay, so this is our first step, second step. This is our third step, right? And then if we do 4 and 5, this is what starts to grow.
I don't understand why do they always flip it?
What do you mean flip it?
Well, like, so, you know, the second row, which was the last step in the example above, right? If you look at the one with the 9, it's flipped.
Yep. So it's just a way of representing them. So this is the computer is doing these computations and it's just graphically representing them. Again, it's arbitrary how they're represented. It's the connectivity information that matters. So there's many ways you can look at this. So if we scroll down, we can see these are different ways to represent the graphs, right?
This is how everything's arbitrary until I say an example and then it's wrong.
What do you mean?
Scroll up. When I was saying like the 4 to 2 to 3, I'm like, how the fuck can that not be X? Like everything, the arrows are arbitrary, the numbers are arbitrary.
No, the arrows are not arbitrary. The arrows are representing the connectivity information. The arrows aren't arbitrary. The way the graph is laid out is arbitrary. The way that they're assigned X and Y and all the rest, that's kind of arbitrary as well. Okay. The connectivity is the important thing. And so all that this rule's saying is if you have a one node of a graph connected to another node of a graph with an edge like that, you can take that and turn it into this connectivity information. Okay, that's all that's saying. So if we scroll down, you've pointed out that you don't like how they flip the graph, whatever. I'm just saying that's just an arbitrary representation. It's the arrows, the connectivity information between each one that matters. Okay. Now, if we scroll down, laying out the nodes differently, you can make it easier to see some of the features of the graph. So you can see that in this one, 1 goes to 2, 2 goes to 3, okay? 3 goes to 5, 3 goes to 9, 3 goes to 17. But it's just showing you that there's this connectivity information. So this is kind of showing you the way the graph grows.
Can you scroll up just a bit just so I can see the one above? Yeah, okay. Yeah, I like the layout of the bottom ones better.
Yeah, so that's more of like a tree structure.
Yeah.
Yeah. So, and that's just different ways. Again, these graphs are incredibly universal. So there's many different ways that we can look at them and lay them out and do all that kind of stuff. The thing that matters is we have this directedness there. There's these directional arrows showing the relation between one bit of graph to another bit of graph. Yeah.
Yeah.
Kind of getting it? So if we continue that for a few more steps, this is how the structure grows. The same rules, same initial conditions. We keep running it. Can you see how this thing kind of starts growing?
Yeah.
Yeah.
Okay. So showing the last three steps with the other layout makes it a little clearer what is going on. So you see these last three graphs, if you lay them out like this tree structure, you can kind of see how from this initial condition or this, X, Y, this thing X to Y, those 2 points there, how from that, if you keep applying this rule, there's all these different possible ways that it can get done.
Okay. I mean, I'm understanding the theory. I just don't understand like what we're talking about. Does that make sense?
Yeah, it's pretty abstract without like an example.
So we're talking.
I don't know what the purpose of this is.
Yeah, that's what I'm getting at.
Okay. Like I can understand these rules, but
so you would never think that something abstract as this and something as simple as this could ever give you something as rich as the experiences that we have in reality. Right? Like, would you think that? Would you think that from like something as simple as like that weird transformation thing that does this, builds this graph thing, that from that could emerge what we experience as reality?
Yeah, currently, yeah.
Yeah, right. It's really abstract. But this is just showing you that if you have this graph structure, so you have these nodes and you have relations between those nodes, and those relations we call edges or hyper edges. It's just the connectivity information. So how a node over here relates to a node over here, right, sort of defines what that is. And so what we're doing with this is we're understanding the base sort of elements that we need to understand to build out this theory of a universe or to understand the universe. Yeah. So what we're doing here is we're sort of understanding the basic steps that we need to understand to go on to see how these simple things, from these simple things, immense complexity emerges.
Yeah, I mean, I understand that point. It's like the Big Bang Theory,
which is. What do you mean, like the Big Bang Theory?
Well, that everything started. Well, if we think about actually Earth before there was any living, before there was like humans and animals, we just had these living organisms. And what was the first one that we started off with? And then came along the mitochondria, I think.
Yeah, so like essentially you have like bacteria and then it keeps fucking around and finds a certain hack in the system, so to speak, and then it evolves into something different, and it's this whole process. Yeah, so we can kind of understand this. So what this is saying is if you just start with like nothing except for these tiny little points and you have all these different rules that can update that graph or be applied to update, the updating sequence is time. Yeah. So as the graph changes, the rules keep getting applied, changing the graph more and more and more. And that's what we perceive to be time. Yeah. And if you run these things for long enough, you can see how they grow and they develop these shapes and structures and all this other stuff. And that's essentially what he's saying is if you go down to the base level, back to the beginning of the universe, it probably started out with, all possible rules being able to be applied with all possible initial conditions. And if you run that from, a start point, so if we look at this graph, that very start point, that X to Y, it just starts growing this immense sort of complexity in this structure. And that ends up resulting in what we perceive to be reality. Kind of on topic.
I mean, I understand. I kind of get it, but I just don't. I'm just trying to. I mean, for me to really understand, it's like I need to connect it to some sort of real life examples. But I guess
so we'll get there. Okay, so think about this, right? What is a seed?
I don't know what a seed is.
So what happens when you take a seed and you put it in the ground and you put water on it?
Right, the seed sprouts.
Yep. And then over time,
takes
depending on
nutrients and it starts growing.
Correct. And so think of a seed as a set of rules, right? It's a collection of rules. Those rules kind of say, if this, then that. Yeah.
Right. So like
if I have nutrients around and I have sufficient moisture and sufficient temperature or photons, then I take these nutrients, I take that water, and I combine them in a certain way to create a structure. And if you run that for long enough, that ends up being a tree or a plant or a flower or whatever. Yeah?
Yeah.
So similar to this, we say we've got these sets of rules that say if there's a certain set of piece of hypergraph that looks like X goes to Y, then you can apply a rule that says X goes to Y, or transforms that from X goes to Y into X goes to Y and Y goes to Z. And essentially they're the same thing, just at very different scales. But that seed is applying, the seed is applying transformations based on its rule set. It's saying that, well, if I have these nutrients available to me and I have this water and I have this sunlight, well, I take these nutrients and I combine them together in this way to produce this structure. And then like you run that enough, the conditions are sufficient. So essentially what you're doing is that seed's embedded in the hypergraph, right? And it's saying, if the hypergraph around you has these conditions, use your rules to transform that hypergraph into this new thing. And that's that new structure that the tree is building or the seed is growing. Kind of makes sense?
Yeah, no, the seed example, I feel that is a good one. Yeah.
We move on?
Yeah.
We've lost JG. I think you're muted, Guy.
I wasn't saying anything. I was just laughing.
Okay. So since order within each relation matters, the following is a different rule. So see how the last rule was X goes to Y and then X goes to Y, Y goes to Z. Now we've changed the way that this new rule says that when you've got X goes to Y, transform it into Z goes to Y, Y goes to X. Yeah. So it's kind of like the inverse. Yeah.
So how are these rules determined? I don't understand that.
Okay. So how are the rules determined? Essentially,
what determines the rules?
Hey?
Or what determines the rules?
So think about it in terms of whatever rule can exist, does exist.
That's a very convenient answer.
Well, so we can get into the maths of it. Like I can show you how to essentially summarize that. So say you have, two objects. There's like a finite amount of different ways you can sort of transform or arrange those things.
Okay. Yeah.
Should we get into the weeds of that?
I don't know where this is going. So if it's derailing you from what you're going to talk about, then...
Well, no, it's relevant. It's a way of answering like who determines these rules or whatever. But essentially, just think of any transformation that can happen. So so with the rules, you've always got we'll talk about them in terms of left side and a right side.
Okay.
And we're saying that the left side is the input and the right side is the output.
Right.
Yeah. And so if we constrain this to you can have two inputs on the left and then you can have two outputs on the right, so say four outputs on the right, two sets of two outputs, then we can look at all possible combinations of that. Yeah. And then we can say, we can do it again. If we've got three inputs on the left, then we can, and it gives us, two outputs with three nodes in each one, then there's a finite amount of those that can possibly exist.
Okay.
Yeah, kind of makes sense?
Kind of.
Okay, so we can get to that. So let's just quickly, we'll get to that in 1 second. So let's just quickly look at this. So this is similar rule, right? Like similar, but the arrows are in a different way now.
Yeah.
See how they're like essentially inverted, like you said, Justin, previously?
Yeah.
So again, like the previous rule, running this rule also gives a tree, but now with a somewhat different structure. So just by changing that rule and just sort of inverting those arrows, do you see how this structure now has changed into a different thing?
Yeah.
Yep. Cool. And so these are the tree representations, right? These sort of binomial trees. And see how they're very different from the other ones?
Yeah.
Yep. Okay, so simple change, very similar, but very different outcomes. Okay, so that's sort of like the main takeaway. Okay.
Are we just going through all the different types of rules?
No. So this is just, I just wanted to give you an overview of like how certain things can arise, like different shapes and sort of structures. And then we can go into the deeper into the rules. Yeah.
Okay.
Yeah. So let's just do this. Yeah. There we go. Okay. So this is an example of a self loop. Yeah. So a relation contains two identical elements, as in 0, 0 or x, x, corresponding to a self loop in a graph. Starting our first rule from a single self loop, the self loop effectively just stays marking the original node. Okay. So that first rule that we looked at, xy goes to xy, goes to yz. So if we apply that same rule here, but with the initial condition of a self loop, this is how it sort of grows out. Yeah. And you can still see that initial condition present in the sort of, at that level of evolution. Kind of get that?
No.
So we're starting this rule from a different initial condition.
I get that. So there's only one loop in the whole structure?
Yes. But then we go down when we change the rule. So when it's the different rule, that inverse rule, remember how we had the first one was all going to the right. And then we looked last page, we looked at this new version of that rule, which is essentially the same rule, but the arrows are directed differently.
Yeah.
This rule says XY goes to YZ and Z goes to X. Whereas in the other rule, it was XY goes to XY and Y goes to Z. Yep. So this is just an inversion of that. Well, yeah, in a sense. Okay. So when you do that with this new rule, so this was the first rule that we looked at, and you see how it grows this kind of tree. But then when we change that first rule to be different, okay, and you apply it with the self loop, it grows this structure.
The self loop effectively takes over the system, inflating to
a 2n gone. So that's just telling you the connectivity information, 2 to the n.
Okay.
Kind of see how that works?
System. I don't understand why it effectively takes over the system. Is it just a rule that I'm supposed to?
No. Accept? So what it's showing you that, like, if you have a rule, so if this is that second rule we looked at, right? If we put the first one in, it grows this tree structure, okay? And that there's only one sort of self loop in that time when you apply that simple rule. But then if we make a small adjustment to that simple rule and we say that instead of XY going to XY, YZ, we say that it's XY goes to YZ, ZX, okay? Then that initial condition has much greater impact, right? It completely changes what ends up happening. So the interaction between that initial condition and that different rule ends up with a completely different structure.
Okay.
So on the last page, I'll just quickly, So on the last page, we saw that this rule, okay, this XY goes to ZY, goes to YX. When you run it, gives you this crazy structure, okay, with this crazy way of representing as a tree. Yep. Then if we have that, take that exact same rule that we just saw on that last page, but we start it from a different initial condition. So we start it with a self loop instead of just starting it with the XY. Yeah. Then we run the rule. This is the structure we get. So same rule, different initial condition.
Right.
That's the takeaway.
Okay. On the last page, it was sort of like a collapsing model.
What do you mean collapsing model?
Well, because all the arrows are going inwards, right? And essentially, it becoming smaller. Like there was like 100 different endpoints, and all the arrows are going inwards. So is that it? Kind of looks like a collapsing model, like it's collapsing in on itself.
No, it'll be growing out.
Am I seeing that wrong? Are the arrows facing inward?
Yeah, some are facing in, some are facing out, right? So there'll be all different connectivity information, but this one grows into this weird structure. Yeah.
Okay.
Same rule. But if we start it from a different initial condition, it grows this. It grows a freaking circle, man. Like it grows a square. It's like, after 3 steps, it grows a square and then it progressively keeps adding edges to that where you essentially are approximating a circle.
Okay.
Yeah. Kind of makes sense. So it's just showing you that from a same rule, but different initial condition means that you get a completely different connectivity, or you get completely different connectivity information. And the emergent sort of graph representation of that is very different.
All right, guys, let's get on to the Belika model next over there, guy.
This one. Starting from a single self loop, this different rule, which says XX goes to YY, goes to YY, goes to XY, represented graphically as simple self loop to start with, grows into this YY self loop, okay, twice, and then an XY connection. So it introduces new variables, which are your Ys, okay, or new atoms of existence. So starting from a single self loop, this rule produces a simple binary tree. Yeah. Again, you don't have to try and understand too much about this. Just kind of look and be like, okay, that's fucking interesting, weird how it grows this different structure. Yeah?
Yeah.
Okay. So let's get into multi-edges. So this is the question you're asking before. So
me?
Yeah. So this is like about your about the different edges, like how come things can have multiple edges?
I was asking about hyperedges, I think.
Yeah, but you also asked about many arrows.
Oh, okay.
Yeah. So rules can involve several copies of the same relation.
Oh, I asked about bidirectional edges. Yeah.
Corresponding to multi-edges in a graph. A simple example is the rule XY goes to XZ, XZ, and YZ. Okay. And so because there's two XZs in that, there's 2 arrows between it. That's it. Like, again, don't read too much into it. It's very simple, very abstract. Yeah. So if you run this rule for a certain amount of steps, it produces a structure with 3 n edges, or 1/6, 3 to the n plus 1 plus 3 nodes at step n. So it just tells you how big the graph grows after each step, essentially. Yep. So this freaky structure sort of emerges from that. It's pretty interesting. And then we get down into multi-edges. So rules can both create and destroy the multi-edges. All right. So this rule here, XZ, ZW, YZ, generates a multi-edge after one step, but then it destroys it again. Okay. So it's just like a weird behavior. And what the whole concept here is trying to get across to us is like these very simple rules can end up having immensely complex behavior that you can't really tell from the rule. Yeah. Like they're really hard to like sort of wrap your head around. You can't really tell that if I run that for 20 steps, I'll get something that looks like this. Yeah. There's no sort of intuitive way for us to see that in our minds. We have to run it to see what happens.
Where does it get destroyed?
Okay, so it creates a multi-edge after one step. So it's got these two connections here. Yeah. So that's a multi-edge.
Yeah.
Yep. And then on the third step, that multi-edge gets destroyed and replaced by different connectivity information.
I see. Yeah, I see.
Okay, cool. So we'll go on because we're about to get to the good stuff. So the representation of rules. The examples we've discussed so far all contain only relations involving two elements, which can readily be represented as ordinary directed graphs. But in the class of models we consider, it is also possible to have relations involving other numbers of elements, say 3. As an example, consider 1, 2, 3, 3, 4, 5, which consists of ternary relations. Such an object can be represented as a hypergraph consisting of two ternary hyperedges. Okay, so this sort of shading here represents a hyperedge that just essentially tells you that these all share a directed edge or relations. Yeah, they all share edges.
Yeah.
Yep. So we can tell that these three things share an edge, and these three things share edges based on the hyperedge. Yeah, hyperedge is the shading.
Okay.
Yeah, makes sense.
Yeah, I see. I don't really understand what ternary means, but I assume
two ternary relations. So 1, 2.
Yeah, I never heard the term ternary before.
Let's get a definition up.
Ternary sounds like three.
Of relating to or proceeding by 3, having 3 elements, parts, or divisions arranged in 3s.
Yeah, okay, I get it.
Okie dokes. Note that hypergraphs can contain full or partial self-loops, as in the example, which can be drawn as follows. So 1, 1, 1, that's a self-loop. 1 goes to 1, goes to 1. 1, 2, 3. So edge 1 goes to 2, goes to 3, and then 3, 4, 4. So 3 goes to 4 and 4 goes to 4. It has a relationship to itself. Yep. Again, kind of random. We're just trying to look at the way these things work. So rules can involve K-ary relations. All that K-ary means is just like any number of different relations. Yeah. So here it's K is just representing any number.
Yeah.
Yep. K-ary is just any number of relations. So here's an example with ternary relations. So these are 3s. Yep. And this rule can be represented as the following. Okay. Very simple. So it's just representing the 3 different relations. X goes to Y goes to Z. X goes to Y goes to Z. And then you can transform that into XYW, XYW, YWZ. So YWZ. Simple. I know, abstract, but don't worry, we're going to tie this all together. Starting from a single ternary self-loop, here are the first few steps obtained with this rule. So it's just showing you how this thing kind of grows. Yep. And then you can continue the rule for the following results. Starts to knit this freaky sort of structure. So it's worth noting that in addition to having relations involving 3 or more elements, it is also possible to have relations with just one element. Here is an example of a rule involving unary relations or one relation. Okay, so X goes to XY, goes to Y, goes to Y. And that's how that would look graphically represented. Those rings are just the self-loops. Okay, starting from an unary self-loop, this rule leads to a binary tree with double unary self-loops as leaves. Okay, kind of like a freaky structure. Yeah?
Yes, sir.
I feel like we've lost you guys. Okay, so you can have rules depending on more than one relation. Yep.
You haven't lost me. I'm just accepting that I'm not going to understand this, and I'm just hoping that
I'm going to tie it all together. I'm hoping to be able to tie this all together. Okay, so Yeah. So a crucial simplifying feature of the rules that we've looked at so far is that they depend only on one relation. So that in a collection of relations, the rule can be applied separately to each relation. Yeah. Or put another way, this means that all the rules we have considered always transform single edges or hyperedges independently. But consider a rule like x, y, z, x, z goes to the following. This can be represented graphically as this. Guy, you pay attention?
Yeah.
Guy, I can see your eyes. I can tell when you're not. Yeah?
Well, yeah, sure, guy. We're just scrolling past all these things anyways, guy.
Yeah, I'm just trying to show you this basic structure so we can then talk about what its implications are later on. Okay.
I know, but I'm not going to remember all these structures.
You don't have to.
75. No,
you don't have to. We're just looking at how very simple thing, these transformations, that when applied to these graphs, you can grow these sort of freaky structures. Okay?
Yeah.
So what I'm getting from all this is that there is just an infinite amount of possibilities. Everything is just infinite.
Maybe. So Wolfram estimates that the universe is a collection of 10 to the 500 of these atoms of space. So these points. Okay. So if you tried to model 10 to the 500, okay, small tangent that I think this could actually work well.
When are we wrapping up this lesson, Guy?
Soon, Guy. Where did I put that?
I mean, it just seems like each time, like we look at one model, right? And it just seems like for the first model, for example, it could just keep growing and growing and growing and growing. And each model sort of is representing that in some sort of way. And just doesn't seem like there's a limit to the possibilities depending on which variable comes in.
Yes.
And which system it is.
Yes. So that's okay. So imagine if you took all possible rules that could exist. Okay. Just like a ridiculous amount of those things, right? Mm-hmm. All those different transformations. If you run all of them, right? If you run all of them, you end up with this object called the ruliad. Yeah. Which is essentially the entangled limit, or it's the superposition of all finite automata. Okay. And automata is just those rules essentially. Right. Or those connections on the graph. Now, if we go back to this, I use this example to try and explain what being computationally bounded is, but this might help, right? So the Wolfram model, the universe is said to be a collection or network of about 10 to the 500 eames. And eames is just his way of saying atoms of space. Okay, so those tiny little points. Now, that's a ridiculously huge number. So for comparison, there's said to be between 10 to the 78 and 10 to the 82 atoms in the known universe. Okay, so this is 10 to the 500 is just ridiculously large amount of things. Yeah. You know how small atoms are. Okay. So if all the atoms in the universe is between 10 to the 78 and 10 to the 82, it's showing that these eames are way smaller than atoms. Kind of makes sense?
Yeah.
Yeah. And so to get an idea of that, it's said that there is 4.6 times 10 to the 23 grains of sand on the earth.
Okay.
Kind of get an idea of how big these numbers are?
Yeah.
Yeah.
You got a spelling error there, Guy?
Yeah, I got heaps. I typed this out very quickly. So if these graphs, they get really big really quick, right? Because of that, they're growing and they're doing all this kind of stuff. And so in order for us to be able to model, the only way to model the universe is the universe, if that kind of makes sense. And because we exist as a subset of these points within the universe, we only ever have access to a small part of that universe. Yeah. So computer chips are made out of sand or silicon. Yep. So even if we took every atom of or grain of sand on the planet and turned it into a computer or computer chips, we could only model things that are 4.6 times 10 to the 23 large. Does that make sense? So all we're doing with those other rules is we're just going through and just looking at like how these very simple rules can exhibit this very complex behavior that's unintuitive from just looking at the rule. The rule's like this really weird abstract thing, but all of this structure emerges when you run it.
I'm going to start making up my own rules, guy.
Okay, so let's go back to the rules real quick. Let's get some of this in. Okay. So typical behaviors, updating process of string substitutions. Let's go through, have a look here. Let's go back here. Okay. So let's just quickly run over this. This is just a decent example. So we've got this really simple rule here, or weird abstract rule. This is what it looks like. Okay. So if we run that, if you run that for 15 steps, right? So if you evolve it for 15 moments in time, so to speak, it grows to being something that has 6,974 elements and 13,944 relations. Okay. And this is the structure that you kind of get. Weird, right?
Yeah.
Okay. So let's try to tie this back to something that we can understand a bit better.
It's annoying how they use different terminology interchangeably.
Yeah, I think that they're trying to do that in an attempt to show the arbitrariness of it.
Well, that is.
But I know what you mean. It can make it quite hard to follow. There's no sort of continuity between.
Yeah, like why bother calling things edges and then calling them relations? Just fucking call them one thing and continue that on. It's already abstract enough. We don't need to add 13 interchangeable terms.
Yeah, I think that's a fair point.
That's another point for you, Steve.
Steve. Guy, I don't know if that's a great way to get him on, but
guy, he's your guy. It's not my guy. Albert was my guy.
Okay, let's go to a pretty concrete example. Let's go here. Wolfram. Okay.
What's this search engine you're using?
U.com.
I've never heard of you.
Wolfram.
Is it better than DuckDuckGo?
Yeah, that's what I was wondering too.
I never heard
Why is it better than DuckDuckGo?
Just significantly better.
Yeah, that's why it's better, right?
Well, okay. So why is it better? Well, it's got better integration. So like it links to things that are more relevant for me, like GitHub and stuff like that. And it does more tailored search results and keeps everything private. They don't sell your stuff to hackers or anyone else. Hey, can we just do a quick wee break?
Sure.
This hopefully should tie it all together.
I was hoping that this was a good point to just wrap her up, guy.
Shortly, okay. I just want to try and get this whole thing back together so we can sort of at least have some stuff to think about. Yeah.
Okay. I have lots to think
break.
About. All right.
Why doesn't Rube just smoke right there? I don't get it. Where's he going?
Oh, he's going to take a piss, guy.
I thought he said weed break.
Oh, he said weed.
Oh, I thought he was saying weed break. I'm like, where's he going? He's gonna go get some from out back, guy. He's gonna cut some off the plant, dry it up.
That's mad funny.
Yeah, I didn't know it was a weed break. Guy, I mean, I feel like we're not contributing to this pod. You know what I mean?
Yeah.
Like, I'm questioning the angle now because I understand like
I also think we're even a shitty audience, guy. Cause like I was I still don't know what relativity or quantum mechanics is. So I'm like, we just kind of skimmed over that.
Yeah, I know. I loved the idea first because I was like, okay, like Ruben's going to take us through this. Our job is just to ask questions, right? Which will give like the audience the opportunity to learn as well, and give Rubes the opportunity to find ways to explain it, to create teaching moments. But man, the
graphing stuff is easy enough to understand. It's just a matter of like accepting though that those are the rules, and you're like, well, okay, I don't really understand how they got to the rules, but if that's what it is, that's what it is then, I guess.
Yeah. And I'm wondering how we got to that number. Like he put like to the power of 500 or whatever it was. Like, I'm curious like how the system is limited to that number.
It's not limited to that number. So that's just like an estimate. What it's saying is that the universe is actually constantly it's expanding.
Okay.
So those atoms of existence, those eames, are constantly getting created, and there's rules that exist that can destroy them as well. But essentially, what's happening is atoms of space or eames are being created faster than they're being destroyed, and that's why the universe is expanding. So there's some cool stuff we can get into about how he did come up with that number, and there's a whole bunch of other implications using what people already know in physics and quantum mechanics and the rest of it. So to try and tie all this together, one good way to think about what he's sort of presenting in this, which is what's called multi-computation. Okay, so there's kind of like been these 4 different paradigms. The third paradigm was just computation, that you could come up with programs to model things in reality. Yeah, computer programs that could model the behavior of systems in reality. And this 4th paradigm is multi-computation. Yeah, and that's kind of like this quantum mechanical, all possible things kind of thing. Yeah. And so a good way to think about that is games, right? So games are sort of multi-computational inherently. And so what makes a game a game?
Rules.
Precisely. That's it. So you define a set of rules. Yeah, you define a set of rules. Okay.
Referees.
Yeah, and so without the rules, right?
Players.
Yeah, but what makes a game is the rules. Okay. And so we can look at a bunch of simple games like noughts and crosses or checkers or any of these other sort of games, and we can plot them out using this sort of graphical framework, right? So he goes through this whole humanizing multi-computation. And so it's one of the core ideas of the Wolfram Physics Project. And in particular, it's at the heart of our emerging understanding of quantum mechanics. But it's hard to get an intuition for what is initially a rather abstract idea of multi-computation. Okay, so we can go through and look at these sort of games, right? So let's have a look at tic-tac-toe. So this is a simplified version of tic-tac-toe or noughts and crosses played on a 2x2 board, right? So very simple to sort of understand. Assume X plays first, then one can represent the possible moves by the graph here. Yeah. So X can go in any one of these 4 quadrants, showing that bottom right, bottom left, top right, top left. That's what it could do. Yep.
4 possible moves.
Yep. Because there's only 4 squares.
So far I'm understanding this.
2 times 2 is 4. Therefore, if X goes first, it has 4 possible positions it can be played in. Okay. So that's the initial condition with no X's. These are the next 4 possible conditions, like states that the board can be in. Yep. Then O goes. And so we've gone from 1 to 4. Yeah. And then from these, there can be these following states. So there's 3 possible places that O can go, not 4 because X is already taking 1. 3 again, 3 again, and 3 again. Yeah.
Okay.
See how this is kind of growing? So
that's easy. This is easy to understand.
Yeah. It's a simple tree. But if we play another turn, we'll see that different branches can merge, and playing until the board is full, we get a multi-way graph or game graph of the form this. Okay. So This kind of explains that we can go down all these different paths. These are all the possible different things that could be played, all the different possible configurations.
Yeah.
Yep. And so from just a 2x2, you can see that like it's pretty complex, but still very understandable.
And really there's only 6 possible outcomes.
Correct.
Oh,
that's
interesting.
6 possible outcomes, right? 6 different board configurations that result in the following.
Okay, that's interesting. Yeah, I'm understanding this so far.
Okay, so every path through this graph represents a possible complete game.
Okay.
Yeah. So every path through the graph results in possible different configurations. Yeah. So if we go down, here, go to here, well, then this can either go to here or it can go to here.
Okay. Yeah.
Yeah. Ending up with different final conditions. Okay. Board conditions can never be reached in any game. Graph 35, the total number of possible complete games, number of possible paths for the graph is 24. If one orders the graph in 3D, one can see that it's very regular structure. So this is rendering the graph in 3D, and this is showing a structure. Yeah.
So already harder to understand in 3D.
This is just showing you the relation, right? These are the edges, the connectivity information. Yeah. It's definitely easier to understand this way.
Yeah.
In 2D. 3D does make it a bit more difficult. You're correct. Okay, so now we define winning the 2x2 tic-tac-toe as having 2 identical elements in a horizontal row. Then we can annotate the multi-way graph to indicate wins, removing cases where the game is already over. Yeah. So this is showing you that the game is already won at this step. This is so 1 step, 2 steps, 3 steps. So in 3 steps, the game's already won. But if you followed these different paths, it would take you 4 steps to get to the outcome. Yeah. So some paths are only 3 steps long. Some paths are 4 steps long.
Oh, so they're saying that 2 X's in a diagonal formation is
horizontal.
Is not,
horizontal.
Right. Only horizontal or vertical combinations win. Or no, sorry, only horizontal.
It's saying horizontal. So this is showing when the game is won, sorry. And this is showing you where the game ends in a tie, right? Where there is no winner. Sorry, I didn't clearly explain that. That's my bad.
No, it's all right. So
so then he goes on to say, much of the core structure of the multi-way graph is actually already evident in the seemingly trivial case of a 1-player tic-tac-toe, in which one is simply progressively filling in the squares of the board. Yep. Simple, kind of arbitrary example. But what makes this not completely trivial is the existence of distinct paths that lead to equivalent states. Yeah. So this is that many possible things, but they end up being the same state. That we were talking about in the beginning. So remember, we're trying to all the possible paths that you could go down, but some of those, some of all those possible paths will end up being in the same state eventually.
Okay. Yeah.
Yeah. And so this is a good example of you could go, so following the cursor, we could go to here, to here, to here, and end up in this state, or we could go from here to here, to here, but they end up in the same state.
Yep.
Yeah. But there's 2 possibilities for that. Yeah. So that's kind of like the branching. So here it branches. Sorry, here it branches, and then here it merges into this one state again. So even though you followed 2 different paths, you ended up at the same point. Make sense?
Okay. Yeah,
Justin?
Yeah.
Funny. Okay. So for a 3x3 board, right? The graph is a 9-dimensional hypercube with 2 to the 9 2 to the 9 equals 512 nodes, and 9 factorial 362,880 game paths, or in move layered form, the following. So you just see like how incredibly complex these structures can get. So we went from a 2x2 board, which we could easily sort of see, to a 3x3 board, and this is the possible, like this, the path graphs, essentially, the possible game states and game paths that you could follow. Yeah,
right.
And
like
he's saying here this basic structure is already visible in one player 1D tic-tac-toe, in which the multi-way graph for a length n board just corresponds to an n-dimensional hypercube. Yep. So n just being a number. So if you start with length 1, it'll end up being a one-dimensional hypercube, 2, etc. n3 equals this, and then n4 is this, okay? And then he goes on to say that the total number of distinct board configurations in this case is just 2 to the n, and the number of distinct games is n factorial. So do you know what factorial is?
Yeah.
No.
Okay, so if you have 5 factorial, you have 5 times 4 times 3 times 2 times 1. If you have 4 factorial, it's 4 times 3 times 2 times 1.
Yes, you are correct, sir.
Yeah. So that number gets big really quick. So like 100 factorial is just a retardedly big number.
Yeah.
Okay.
It's sort of just showing you how it scales. With 2 players, the graphs become slightly more complicated. We can sort of see how this kind of works. Yep, go down. So the total number of states in these graphs is after certain steps. So 2, and then it goes to 5, then 13, then 35, then 96. And so you can just see how, like, as you move on, the possible states just grows ridiculously. And so this is showing that it's asymptotically, it grows like 3n to the negative half over square root of pi n. Okay.
Let's watch a little Google on that word there, guy.
Which? Asymptotically?
Yeah. Try to pausing it.
I think it's like an abstract representation. I can't spell that.
Approaching a given value or condition as a variable or an expression containing a variable approaches a limit, usually infinity.
Yeah, okay, sorry. So yeah, as it approaches the limit, it ends up resembling this. Yeah, so in the limit, this is what it ends up being. Yeah, so you can classify that as this equation. It essentially just tells you how it grows. Note that for n equals 4, the result is the same as for the 2x2 board discussed above. And at move t, the number of distinct states is given by the following equation. Okay, so we can sort of see how this goes up. Yep, so there's only 126 different configurations after 9 and 9. So then let's have a look at a standard 2-player 3x3 tic-tac-toe. It's kind of, does this make the kind of making sense? How these things, how like the graphs correspond to this kind of stuff?
I have a feeling it's about to not make sense when I'm seeing the bottom there.
Oh, okay. No, this is cool. This should bring this all together. Okay, so what about a 2x2 2-player 3x3 tic-tac-toe? Its multi-way graph begins, initial condition, no pieces done. So then out of all of that, there's essentially going to be 9 possible configurations for the board. 1, 2, 3, 4, 5, 6, 7, 8, 9 possible starting or next moves, right? After 2 steps, i.e. 1 move by X and 1 move by naught, the graph is still a tree with the initial state now at the center. Okay, so this is the initial condition.
Mm-hmm.
Yep. And these are the next possible conditions that it can go from. And if we count it out, there should be 8 nodes on each of these. Yep.
Yeah.
So from that state to that state, and then there should only be 8 spots left on this here to fill. Does it make sense? Because X is going to be moving to here. And so let's say this one here represents this one here. Okay, so X is down in the bottom right. That's representing here. And then there's 8 possible places that naught can go to.
Yeah, that makes sense.
Cool. So after 3 steps, this is the sort of graph that we start to get. There is starting to be merging. See how different paths will end up with the same board configuration?
Mm-hmm.
Yeah, and that's the merging. So when it merges, the paths went a different way, but after another step, they ended up being in the same configuration. Even though it was a different path they both took to get to that same configuration.
Okay.
Kind of making sense?
Yeah, it does make sense.
Yep. So the example is I'll scroll back up. The example we can use is this one here, where if we followed this path to here, then to here, then to here, we got this board configuration. But we also equivalently could have gone from here to here to here and ended up here.
Right.
So 2 different paths, but they both ended up at the same configuration of the board.
Right.
Yeah.
Cool?
Yeah.
Okay.
It's much easier with an example.
Yeah. So maybe we should have started here. My bad.
Nice job explaining this part, Rubes.
Thanks. And continuing for all 9 moves, the fully layered graph with 646 states is the following. Boosh. So each point, you could think about each slice, right? So see, we've got starting position or starting from nothing. And we've got the next possible configurations. Okay. Then another move, we've got the next possible configurations. Then another move, right? And you can think of this as time, right?
Isn't it crazy that there's all those possibilities, but if you play with anyone that's older than like 7 years old, it's always a draw?
Yeah. No, so yes, so this is where so if you just look at these models, you think like, oh my God, this is overwhelming. But then when you take into account certain things, you realize, oh my God, it's actually really informative because like some of these paths are kind of like irrelevant. You know what I mean? Like there are definite sort of common paths that people tend to follow when they play this game.
Right.
And so you don't need to explore sort of all of the search space. Like if you're trying to get good at this, you could just explore like what are the common moves that people normally do. Right? Like you can also then use this graph to show you like all the different ways you can get to the configuration you want. And if you understand how to get to the configuration you want, you can win the game every time.
I don't know, man.
What do you mean?
I reckon if we play to be a draw.
Well, there's ways to play where you can force the player to make a move, which gives you 2 possible
wins. Yeah. So that's what I'm saying is like, if you understand the way that this graph flows, you can do moves that sort of end up guaranteeing that you'll win. Yeah.
Yeah.
Okay. So, we get this. Yep. Cool. Okay, so then he goes on to say, at the level of this graph, the results are exactly the same as for a 2-player 1D version with a total of 9 squares. But for actual 2D 3x3 tic-tac-toe, there is an additional element to the story. The concept of winning a game and thereby terminating it. With the usual rules, a game is considered won when a player gets a horizontal, vertical, or diagonal line of 3 squares, as in, for example, the following conditions, right? So you can see that this is after all steps they win, and there's only 4 configurations, okay, for that to be the case. Yeah.
Yeah.
And then this is after 8 moves. There's also only 4 unique configurations. After after 7, there's also only 4 unique configurations. After 6, there's only 4 unique configurations. And after 5, there's also only 4 unique configurations, which is kind of interesting. Yeah?
Yeah.
Sort of, maybe. Okay. So whenever
it is interesting.
Right. Yes. So you could look at like, okay, what possible board configurations lead to this outcome? Because that's what I want. And so you can sort of understand that, right? There's a bunch of stuff to do. What the hell is Justin doing? Like weird acrobatics?
No, I'm sitting down. Right?
Guy, you look like a midget. I mean,
I've been standing this whole time.
Ah, okay. You don't have a motorized desk?
Yeah, I do.
Oh. Okay, so whenever a win state such as these is reached, the game is considered over, so that subsequent states in the multi-way graph are pruned, and what was previously a 6,046 node graph becomes a 5,478 node graph, so slightly better. Okay, so this is just showing you the possible win states down here. Yep.
Mm-hmm. Yeah.
Okay. With examples. Hey.
So sorry. I think I missed something. So not much, but there's fewer win states. Is that what it said up there? Sorry.
No. What they're saying is whenever a win state such as these is reached, the game is considered over, so that subsequent states in the multi-way graph are pruned. So what this graph up here was showing was like all the possible configurations. But if we take into account that like some of these steps up here, like a step here or a step here could result in a win state.
Right.
Yeah. And so what they're saying is in this next graph, they've pruned all of the subsequent graphs that would follow. Once it's got to a win state, they're going to just prune all those other edges that were on there. So this graph here is a lot denser than this one down here. They've pruned a lot of the connections out.
I see.
Because they're arbitrary. Once you reach, we only care about the win states. So they're taking off the unnecessary.
I see. Okay.
So with examples of the 568 prune states, including where the win that terminated the game is marked, wins can occur at different steps, anywhere from 5 to 9. So now you can gather information about the game, like, oh, okay, so you can only get to a win state from between 5 to 9 moves. Yeah. So unless you're playing against someone that's like really, really silly, you can't get a win, or actually, no, it's just saying, mathematically, you cannot win until at least 5 states or 5 moves have been played. Yeah. And so then it shows you the total number of distinct wins are as follows. So 0 for 1 move, 0 for 2 moves, 0 for 3 moves, 0 for 4 moves. There's 120 possible win states for 5 moves. There's 148 for 6, 444, 168 for 8, and 62 for 9. Nice, guy. Was that a fart?
No, it's a chair.
Hey, of course it was. That's what Becky says. You're using 626 wins at any step for X and 316 for 0. So it's saying that if you start, right, if you're X, you've essentially got like double the chances of winning than 0 does. There exists twice as many, or almost twice as many possible win states for you if you go first versus go to 0. Kind of makes sense?
Yeah.
Okay.
Yielding 626 wins at any step for X and 316 for 0.
Yeah.
With when there's between 5 and 9 moves.
Yeah.
Right?
Yeah. And so then it just goes on. One can't explicitly tell that a game has ended in a draw until every square has been filled in, and there are ultimately only 16 final draw configurations that can be reached. Yep. So we can see that there. You can annotate the full game over pruned multi-way graph indicating win and draw states. So that's those listed in there. To study this further, let's start looking at a subgraph that includes only endgames, starting with a board that already has 4 squares filled. So starting at 4 squares filled, you can go over and you can see these are the final possible configurations. So this is just a way of pruning the graph to keep, information that's relevant to us in this respect. Pretty simple, yeah? So he hammers this home a bunch. But one of the things that he says is, so it's possible to get a final win for both X and 0. So from this configuration here, it is possible to get a final win for both X and 0. But in many of these cases, the outcome is already basically determined a step or more before the actual win occurs. In the sense that unless a given player makes a mistake, they will always be able to force a win. And that's kind of that condition you were saying before, Justin, about like it always ends in a draw kind of thing. Yeah.
Mm-hmm. Yeah.
So then, and it's just saying that like if you follow different paths, you can end up with different outcomes, and you can represent pre-forcing of winds by coloring subgraphs or in effect light cones in the multi-way graph. Okay. So light cones is a really important concept in physics and in the way that we perceive reality, the way that it is. And so like we can only, it's kind of like your degrees of freedom, so to speak. What's a good way to bootstrap this in? You guys ever heard of a light cone?
Negative.
Okay.
Negative.
So light cone. Here we go.
Is it the surface describing the temporal evolution of a flash or a light in minuscule space-time?
Minkowski space, yeah.
Is that what it is? Oh,
yeah.
wow.
Minkowski space-time. But Minkowski space is just think of it like just normal space-time, right? So this, can you see this graph?
Yeah.
Yeah. So think about this as all your past, right? Coming in this bottom light cone. This hypersurface of the present is where we exist. This is the observer in here. And then this is your future light cone. So that's sort of all you have privy to. And so outside of this light cone is the whole rest of the universe. And inside that light cone is all that you can see and causally affect. Yeah. And so he's linking that back to Wolfram. He's saying that we can represent the forcing of winds by coloring subgraphs or in effect the light cones in the multi-way graph. And so what it's saying is if you get to here, there's only a certain direction of ways you can go from this point, right? So this is probably a better example, right? So if you're here, right, you can go to this way, or this way. But if you go to this way, it ends up being a win. So in your light cone, if you get to here, there's only 3 possible choices you have.
Yeah.
Kind of makes sense?
Draw or something?
Eh?
What's purple draw?
Yeah. Well, I think that's, possibly.
Maybe not.
Yeah. They should have a color code for it.
I assume it's not a draw because you'd think there'd be more purple.
Yeah. So, okay, if we start at this position, the light cone is all of this graph. Yeah. But as we make decisions and move down the graph, our light cone sort of gets constrained. And so the analogous thing in your life is think about like, you're born and you have all this possibility. Then you start making decisions and start, behaving in certain ways, learning or not learning certain things. And you're sort of, expanding or shrinking or changing the direction of your light cone, which is just the degrees of freedom in the future, or possible degrees of freedom in the future. Kind of make sense?
Yeah.
Yeah, I think so.
You guys, it's hard, the abstract stuff, right?
Yeah, it is hard.
It's much easier when you can understand what the fucking outcome is supposed to be.
Yeah, that does make a difference. Okay, so let's go through and have a look at this. Annotating the whole multi-way graph, we can think of the graph as representing representation of the solution to the game, given any state of the coloring the graph does. Yeah. So yeah, this is just other ways of coloring this, and it's essentially giving you information as to like who can force a win at what point.
Yeah, I'd really love to know what the purple and the orange are. Supposed to represent.
We can infer that. Okay, so the orange is X makes moves, the purple is 0 makes a move.
It must be just who wins, X or O.
Yeah. Or who can win.
Oh yeah,
I think it's who can win.
That does make sense because there would be a lot more wins with orange because orange went first.
That's right. Yeah. So I think orange is who can win and purple is when it can win.
Yeah.
Orange is when X can win. Purple is when O can win.
Yeah.
Okay. So we're kind of getting this?
Yeah. Yeah.
Yeah.
So then he keeps going on and evolving the states. In general, the number of connecting components on successive steps is as follows. And so there's all these rules. And these are broken down across different graph structures as follows. And so there's all these different graph structures, blah, blah, blah. He goes on for more and more. Okay, so then within the branchial graph.
Why the fuck do we have to do this shit when he's already got the lines up top there? That makes sense.
Oh, okay. So this is, okay. So sorry, I skipped 2 things. Okay, so here we just count the number of possible states, various kind at each step. Okay, so we'll start from here. So here we're just counting the number of possible states of various kinds at each step. So this is this branchial space, yeah, the possible states. But is there a way to think about these states as somehow being laid out in game state space? Branchial graphs provide a potential way to do this. The basic branchial graph at a particular step is obtained by joining pairs of states that share a common ancestor on the step before. Yeah.
Hold on, let me read that again. Basic graph. Okay.
So if we go down, we can see this branchial graph.
Okay.
Yeah.
Yeah.
Potential configurations.
Yeah, I see it.
Things get more complicated for ordinary 3x3 tic-tac-toe, but since the multi-way graph for the first 2 steps is a pure tree, the branchial graphs at these steps will have a rather trivial structure. Okay. Yeah. So these are the possible different configurations. And then again, more so, and there's these connections are showing us what possible states are what states are possible.
This still seems redundant. Like, if you can represent it the way he's been doing it up there, why bother doing this other fucking configuration?
Okay, we're about to get to that. Ready? So he's talking about the connections between. So in general, the number of connected components on successive steps is as follows. Right, so it's just showing you the connectivity information and how this kind of scales. Yeah.
Yeah.
And so then you can see, like, at 1 move, this is the sort of branchial graph you get. At 2 moves, this is the branchial graph you get. At 3 moves, this is the branchial graph you get. At 4 moves, this is the branchial graph you get. And it kind of goes on like this. Yeah. And then it kind of comes down to these, right? So here, and this is kind of like the outcome, like when someone wins, I believe. So here in more detail are the forms of the typical components of branchial graphs achieved at particular steps. So just showing you this. Okay, so then we get down to here. Within the branchial graph at a particular step, there can be different numbers of wins in different components. Highlighted in orange. Okay, representing wins in the game state. Orange is for X, purple is for O. We can go down.
Gray ones.
Okay.
What are these gray ones?
Down here.
No.
I think that might represent a draw.
Up top. 36, 9, 9.
I'd say that's not resolved. So there's no win, no win, no win, no win, no win. So 1 step, 2 step, 3 step, 4 step.
Oh yeah.
Once you get to 5 steps, you can have a win, a win, a win, a win. But an O can't get a win until 6 steps.
Right. Okay, that makes sense. Because up top they said that you couldn't win until the 5th step, right?
Yeah.
So,
Yeah. Okay, so this is kind of coming together.
Yeah, that makes sense.
Okay, so it's notable that wins are quite broadly distributed across the branchial graphs, and this is, in a sense, why tic-tac-toe is not more trivial. If just by knowing what component of the branchial graph one was in, one could immediately know the outcome, there would be even less suspense in the game. But with the broad distribution across branchial space, knowing roughly where you are doesn't help much in determining whether you are going to win.
But with broad distribution across brachial space, knowing roughly where you are doesn't help much in determining whether you're going to win.
Yeah, but because like branchial space is so densely packed, it's kind of hard to tell that. But if it wasn't, you'd easily be able to tell that you could win. Like if the game was simpler. Yeah. So if we took the 2x2 board, you could pretty much tell if you're going to win. You know what I mean? Like there's only 4 steps.
Okay. So
I mean, things like you can do things to make it easier to see.
Yes. And that's sort of what he's saying. Yeah.
Like color.
Yeah. So far, we've always been talking about what states can be reached, but not how often they're reached. Imagine that rather than playing a specific game, we instead at each step just make every possible move with equal probability. The setup for tic-tac-toe is symmetrical enough that for most of the game, the probability of every possible configuration at a given step is equal. But as soon as there start to be wins and there is a cone of game over pruned states, then the remaining states no longer have equal probabilities. This ties into this sort of Judea Pearl paper that I sent through as well. Kind of makes sense.
Yeah.
So we're almost there, boys. We're almost there. Just stay tight for one more minute. Okay, so we can go through the several classes of final states with different probabilities. So you can just sort of like pushing out the probability. So you can know that like what this is essentially saying is if we study the game this way, we can understand the game at a much higher level. We can understand that certain moves have higher probabilities of resulting in wins. Certain game board configurations will bias X winning or O winning. And so if you're X, then you'd want to avoid certain ones that increase the probability for O winning. If you're O, you want to decrease the probability of X winning. So you'd avoid certain game states, essentially informing how you'd make moves. Yeah?
This all makes sense. Yeah.
Okay. So we can go through a bunch of this, a whole bunch of unnecessary examples. There will always be an arithmetic progression. Tie. Okay. Do we want to do walks and their multi-way graphs? Now we'll leave this here. I think it gets much more complex.
We're still talking about tic-tac-toe even down here.
No, he's explaining walks now. So you can see, like walking through a maze.
Oh, okay. Yeah. Okay.
So as far as traversing this maze is concerned, is equivalent to walking on the graph. Okay. So you can represent it as a graph, which is another embedding is just the following. So these are all the different paths you could take to end up out of the maze. Yeah.
Mm-hmm.
Okay.
Cool. So this path through this maze corresponds to this path through this tree.
Correct.
Yep. And there's many possible paths that you could take to get out from the maze, I think.
Well, it looks like there's only 2.
Yep. 2 paths.
Or, yeah, at least 2, I guess. Yep. Unless the other one doesn't lead out, I guess.
Yeah, I don't know if these are representing final destinations or not, but we could just by looking at this graph, we could study that. Yep.
No, I think you're right. I think there's only 2 possible ways, because if you look at the nodes on the shorter ones, there aren't enough possible nodes to get out of the maze. Like points, right?
Yeah, I think you're right. So then these are just other games and essentially how you can depict them and the structures that they form and all the rest of it. Okay.
Shit, guy. That one's a soccer game.
Hey, the icosahedron game.
Right there, guy. Soccer. There's soccer right there.
Do you want to look at that?
No.
Okay. That's what I thought.
I'm ready to shut her down, guy.
Yeah, I can sense that. Just give me 1 second. Have a look at this.
Justin, you going to watch the Japanese Grand Prix?
I missed qualifying, guy. Did you watch qualifying?
No, I just watched the highlights. I think it was Verstappen that foshed it, but he did something really strange, actually. He was supposed to get out of the way for somebody, and he turned right in onto the driving line. It was
Really?
And he forced, I can't remember who it was, but he forced someone off the track, and I think he got in trouble. Well, he for sure got in trouble for that. I just don't know.
Doesn't matter. He can start like a lap behind everyone and still win somehow. Doesn't even matter. Ferrari will pit for no reason.
It starts in 38 minutes.
Oh shit.
Okay, so let's summarize so we can finish up. So initially we went through the different types of graphs. Yeah.
Mm-hmm.
So these are the spatial graphs. These are the causal graphs, right? Essentially, like, this game state can then lead to this game state or this game state, which could then lead to these game states, that kind of thing.
Yeah.
Yep. And then we had the multi-way evolution graph, okay, which is essentially like all the different possible states that the game board could be in after each move.
Correct.
Yep. Oh, that was the branchial graph. Sorry, that's holding all the potential states. And then this multi-way causal graph is the sort of full depiction of all of those things. And we can break this up to get every other graph out of this graph. Okay. So when we go over and we say the Wolfram model, where was my summary? The Wolfram model does not use continuum description of space-time with the Lorentzian manifolds. Instead, it is based on combinatorics of relational properties of events. Okay, so what they're sort of saying is when you start with this very minimal thing, like very minimal assumptions, all that they're saying is that there's these points throughout space, all that exists is space, okay? And that everything that we observe and see and do, whatever, is emergent from the simple rules being applied to that graph over and over and over, wherever they possibly can be applied. Does that kind of make a bit more sense now that we've gone through some of the examples?
Yeah.
Sort of.
So what's, just quickly, so we can, go overview that. What is it sort of like? What's the hard part, or what's the thing that doesn't seem to be as clear as it could be?
It's mostly because I was zoning out when you were talking.
Yeah.
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 Yeah, that's it, guy.
Okay. I don't really know what to do now.
We just shut her down, guy. We just go through this all next week, guy.
Yeah.
The way you said that was mad funny.
It's called mad sarcasm. That was maximum sarcasm. But like, just to be serious for a second, like, yes, you might have been zoning out while talking, et cetera, but like, like, it's hard for me to explain because like, when you read over things so many times, like you start to, you develop your own understanding, but I take many things for granted, like it's that curse of knowledge. Like I sort of know what I know, but I don't know what other people don't know. And so you use a term, it might not be a familiar term. You've looked at a concept many times, so you sort of understand it. So then, but you forget what you didn't understand initially. That kind of makes sense. So I'm just trying to, like, when you say, it's because I was zoning out when you're talking. I'm trying to extract as much value from that statement as possible, but it's like there's without knowing sort of more specifically where the understanding stops or where it starts. It's hard to iterate on that.
Basically, the things that I understood was the rules and the most of the XYZ shit. And yeah, I think the example of the tic-tac-toe makes things way easier because you know what the game is and you know what the outcome is supposed to be. So when you talk about these models and systems without an outcome, it's hard to understand what the fuck you're trying to get to.
Well, so the outcome is our universe and what we perceive and experience.
Means nothing to me, guy.
But that's what you can know.
If I know I need to get 3 X's, guy, or 3 O's, we're good to go, guy.
That X and O example did make it a lot more easier to understand, that's for sure.
Okay.
I mean, and the concepts I'm grasping somewhat, but obviously there's some.
So
I just need like more time.
Yeah, no, I get it. I'm just trying to gauge where we started and where we finished. That's all. Like what things are more clear and what things are still less clear.
So with the tic-tac-toe example, we only saw like straight edges or straight relations or whatever the hell. But we saw like, you know, like the circle ones and all that shit. Eventually, are there like, what was it just that the tic-tac-toe example was simple and didn't include any of those other types of rules? Or
yeah, because of the way the rules that are defined to create the game of tic-tac-toe, that doesn't exist in those rules the ability for that to happen.
Right. So we would get into more complex models, or I don't know what do you call them?
Yeah.
Pathways or
more complex
graphs.
Yeah, more complex graphs or more complex structures. But it's just showing you that like when we see a game, we just see the game and we just see those sort of board states. But when you think about it and you think about it in this way of like, oh, there's actually all these other possibilities of board spaces. We only ever see one really. Do you know what I mean? When we play, we see the one that we see. But there still exists the space of all those possible boards being laid out.
I think about it more in the probabilities way that in the tic-tac-toe example, just because that's how we would present something like that in like a paper or something. Like if you're showing pathways, you'd probably show like an R value or something like that, and it'll show you the strength of the relation between nodes.
Yeah. Absolutely. But it's just a way of representing that game. So start with simple rules and it's defining the space as to which things can happen in. Yeah. And the different outcomes that can happen based on those rules. So that's why it's a bit of an easy example. So remember initially we were talking about general relativity and quantum mechanics and the difference between them and how they don't make sense.
Yeah.
Okay. So when you go through and you sort of see the totality of this whole thing, the statement that can be made is that quantum mechanics and general relativity are actually the same thing. Okay. So they're actually the same sort of theory, but it just happens that when you look at things, depending on the reference frame to which you look at or what you choose to look at, dictates what you see. And so the following is a very good summary of that. And I hope that this should tie a lot of things together. So general relativity is the approximation you get when you ignore the multi-way structure and just look at the hypergraph evolution.
Okay.
Does that make any sense?
Which one was the hypergraph for evolution?
So the hypergraph was the
figure ones rather than the tree ones?
Yeah. So the hypergraph is essentially like the causal relations. You know, it's the higher level graph. Yeah. And the multi-way structure is all the possibilities. The multi-way graph is all the possible ways that it could go. But
when there's no rules.
No, when there is rules.
Sorry, I was thinking because the hypergraph is when you ignore the multi-way structure and you just look at the hypergraph evolution.
Yeah.
Because the hypergraph evolution is more of the tic-tac-toe example, or would it be the multi-way structure?
Let's take tic-tac-toe as the example. Okay. So in this example, the hypergraph, right, would just be the board states that were played.
Yeah.
Yeah. Just the ones that were played. Whereas the multi-way structure would be all the possible board states that there could be. So do you want me to just quickly, okay. I'll just go back and I'll flash an image of this. Okay. So think of, sorry. Okay. This is the multi-way graph. Yeah.
Okay. Yeah.
Showing all the different possible configurations of the board. Yeah. Let's find.
And the hyper one is just with like the infinite amount of crazy lines. Oh, they're the gray one there.
No. So the hypergraph is essentially, what does happen. So if we just followed, like one of these paths. Yeah.
Oh, okay.
It would just show us this path, right?
Okay. Yeah.
And then the multi-way graph is kind of like, this whole thing.
Oh, okay. Okay.
Yeah. So see how there's all this branching and then there's all this merging.
Yeah.
Right.
Okay. And so that's saying that general relativity is when you don't look at this graph, right? You just look at the graph that shows you the path.
Right.
Right. So if we just had a graph that showed us a path to the win, right? Which would just so if we just take this, for example, we go here to here, to here, to here, to here, to here. If we just looked at that evolution graph, okay, we'd perceive general relativity. This is cause and effect, right? It's just showing that this event led to this event, which 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 led to me winning.
Okay.
So you could only tell this causal history.
And that's the hypergraph.
Yeah, essentially. So if we took everything out, that would just be the hypergraph.
Why wouldn't they call that like partial graph or something?
Well, that's what this is. That is a partial graph. Again, we're sort of getting down into the weeds of the words, but this is speaking at a much broader scale. I'm trying to pin this down into a specific example for the tic-tac-toe without generating those graphs myself. Okay, so he doesn't have a clear example just there. I was just trying to use that graph as an example.
Okay.
General relativity is the approximation you get when you ignore the multi-way graph and you just look at the hypergraph.
Evolution, yeah.
Okay.
Yeah. So you can infer cause-effect relationships, essentially.
What word did I lose? Oh, the hypergraph evolution. Sorry, Justin.
No, I'm just saying it's literally the opposite of how I would have guessed.
No. So then read this, right? So then quantum mechanics is what you get when you ignore the hypergraph structure and just look at the multi-way evolution. So remember, quantum mechanics is weird. Everything follows all possible paths.
Right.
Yeah. So in quantum mechanics, if you ignore the hypergraph structure, which is like what we see at a high level, these cause-effect relationships, right? And then you zoom down and you just look at the multi-way evolution of tic-tac-toe, right? You see quantum mechanics. You see all these possibilities. You see the board following all the possible ways the board could go.
Yeah.
Which is this.
Yeah.
Yeah. So this is the multi-way graph. So if you look at this, the multi-way graph, right? When you're at that level of quantum mechanics, this is what you're seeing is happening. Like all these possible things are happening. But if you zoom out sufficiently far, right, you can sort of see that all that really happened, fucking hell. All that really happened was this.
Right.
Yeah. But if you zoom in close enough to this, you see all the possible states.
Right. Okay. So general relativity is the approximation in when we look at what's that?
Is that Reginald?
Negative. It's not me. That's Polska.
No, it's a dog in my neighborhood. Okay, so the general relativity is approximation you get when you ignore the multi-way structure and you just look at the hypergraph evolution, whereas the quantum mechanics is what you get when you ignore the hypergraph structure and just look at the multi-way evolution. Okay.
Yeah. And
good job, Rubes. I got it.
Yeah, I think I understand that as well.
And QFT, quantum gravity.
Guy, let's just stop there, guy.
No. This is what ties it together. QFT, quantum gravity, is some mix of the two. Okay. So when you combine both of those together, essentially, like once they figure out how to how these things, the implications of these things interacting, you'll get quantum gravity. and you'll be able to explain quantum gravity. And that's like the biggest unsolved thing currently, right? No one's done that. But what like the craziest thing is to realize is general relativity and quantum mechanics are essentially the same thing, but just like looking at a different way of looking at it. So when
I understand both of those points there.
So yeah, so when you ignore the multi-way structure and you just look at the hypergraph evolution, you just see like the cause and effect kind of stuff. And so that's where you see general relativity. But then if you ignore the hypergraph and you just look at the multi-way evolution, that's quantum mechanics. And that's all that branching is like the photon goes in every possible way it can go. It follows every possible path the photon can follow.
What's QFT again?
Quantum field theory.
Okay.
Which is a mix of the two.
Well, so yeah, quantum gravity is some mix of the two. So like if you can combine those two together, you can solve quantum gravity.
Okay. All right. Rubes, well done, man. Well done.
Thanks, Polska. But yeah, like again, it's inherently difficult to start with because of the abstractness of it all and how strange it is considering how we normally, like what we normally perceive and exist at and the way we normally talk. But I don't think this is going to make a fantastic episode to start with. I think it could be some great clips that come from this, but it's sort of like getting into this sufficiently will allow us to understand so much more about everything. And so like I said, this is specifically applicable to like everything that there is. Like this is the most universal model that there is so far. And this is kind of, hey?
I was just saying, no, go ahead.
So this is like, most people think mathematics is kind of like the base layer. So this is below mathematics, right? And so, there's the Pythagoras theorem.
Yeah.
Yeah. So the Pythagoras theorem is kind of like a zoomed out thing. If you use combinators, which is like these simple rules or transformation rules applied to stuff, it's about 10 to the 30 of these transformations that you need to do to get Pythagoras' theorem. So Pythagoras' theorem is really simple for us, but it's like a high level view. And if you actually dig into Pythagoras' theorem or you try to prove it, there's like 10 to the 30 different transformations that have to be performed to prove it. And again, that's a huge number. Does that kind of make sense? So like as you come up in scales, once you get to a certain scale, you can like take something that's many different parts and just say it's one thing. So how like you've got all these different cells in your liver, but if you zoom out, you just look at the liver, you go, oh, that's a liver. But the liver is actually made up of all these little parts.
Right.
Yeah. So it's the same thing. But this is like the base level of everything. And that's why it's very hard to understand, because at the base level, it's like none of the things that we take for granted are obvious, right? They all emerge out of this. They're not present in there. So it's really abstract and hard to understand in that regard. But you feel as if we did make some progress.
Well, if the point of this subject was 100%. To understand those two lines, then we've succeeded.
That's what the applause was for, guy. I thought it was well done, Roops. I actually got something out of this. Thank you. I
am slightly concerned that once we stray away from the tic-tac-toe example, then it's going to be fucking hard to understand again, though.
No, it's really, really simple. Honestly, it really is. It's just like getting your head around certain concepts. And so I got a bunch of things like the key concepts to sort of go over. And then like, overviews and stuff like that. But I think what it does is it actually gives you the tools to really think about these things. So when you know that like quantum mechanics is just like observing the multi-way structure, which is the possibility space for given sets of rules, right? It makes quantum mechanics seem like way easier to understand.
Yeah.
You know what I mean? Like it gives you a way of actually understanding it and relating it to things. When you understand that that's actually what quantum mechanics is. Quantum mechanics is when you're looking at this multi-way structure of all the possible things that could be happening.
I have a story to say, but I don't want it to be recorded.
Okay, Rubes, do you want to say one last thing before I stop recording?
No, I'm pretty good. I think as long as we feel as if we made some progress, I'll be happy.
I mean, at the beginning, I had no idea what general relativity or quantum mechanics was. And now I feel like if someone asked me, I could do like a pretty shitty explanation, but I could do one.
Okay, cool. Justin, final comments?
No, I'm the same as Polska, where like, I don't know general relativity or quantum mechanics, but like in the context of this lesson and those two examples, I understand how we got those, like those definitions.
Yeah. Sweet.